Hello there, and welcome to the Sleepy Scholar, a place where we let curiosity drift at a leisurely pace, allowing science to guide your mind into a state of deep relaxation. Tonight, we are traveling to a destination visited by very few, a location that exists on the edge of human experience, even though its name is known to us all. It is a feature of our very own world, yet it seems as distant and enigmatic as the craters of the Moon or the red dust of Mars. This is a place of profound depth, absolute darkness, and such alien conditions that for the vast majority of our history, it existed only in the realm of imagination. The Mariana Trench, the deepest abyss on Earth. Before we begin our slow descent toward those shadowy waters, I would like to ask you a question. Where do you find yourself listening from tonight? Are you near the coastline where the ocean rhythmically breathes against the sand? Or are you far inland where the sea is nothing more than a distant memory or a dream? Perhaps you have stood at the water's edge watching the waves roll in one after another, wondering just how far they stretch and how deep the floor truly drops. Or perhaps the ocean is something you know primarily through stories and images on a screen. Regardless of where you are, right now, you and I are about to drift together into a region of that vast blue expanse that almost no human eyes will ever behold. It is a strange thought, isn't it? The majority of our planet is cloaked in water, yet the landscapes beneath the surface are less familiar to us than the geography of distant planets. If you find comfort in these slow, meandering journeys, explorations that invite you to learn, to wonder, and perhaps to doze off along the way, I would be truly grateful if you liked this video or subscribe to the channel. It helps this quiet corner of calm reach others who might be in need of a gentle pause in their day or a soothing companion for the night. Thank you for being here, and thank you for bringing your curiosity with you. Now, let us begin to let go of the surface world. Picture yourself standing at the shoreline for just a moment. The horizon appears wide and serene, perhaps interrupted only by a distant ship or the flight of seabirds. But beneath those rolling waves lies an entire universe stacked in vertical layers. Imagine swimming downward, passing through the familiar sunlit waters where fish dart among colorful corals. If you continued your descent, you would pass the point where the sunlight fades into a dim blue twilight, where forms become indistinct and colors wash out into grays. Keep going deeper, and even that faint glow disappears. This is where the true deep begins, a realm of permanent, unbroken night. And if you possessed the endurance to continue sinking far below even that silent darkness, you would eventually arrive at a massive tear in the ocean floor, a wound in the very crust of the earth plunging deeper than Mount Everest stands tall. This is the Mariana Trench. It sits quietly in the western Pacific Ocean to the east of the Philippines and south of Japan, curving like a magnificent scar across the seabed. It stretches over 1,500 miles in length, roughly the distance between Los Angeles and Kansas City. However, it is its depth, not its length, that has captivated the minds of explorers and scientists alike. At its most profound point, a spot known as Challenger Deep, the trench reaches nearly 11 kilometers below the surface of the sea. That is approximately 36,000 feet. If you were to take Mount Everest and place it at the bottom of this trench, its summit would still be submerged beneath more than a mile of water. Pausing to consider that number for a moment, it is difficult to even conceive of what that volume of water overhead would feel like. The pressure at those depths is over 1,000 times greater than the atmospheric pressure we feel at the surface. It is a force capable of crushing a human body in an instant, collapsing solid steel and compressing air into something entirely unrecognizable. Yet somehow, against all probability, life has discovered a way to persist even there. But I am getting ahead of our story. Before we drift too far into those depths, It is worth remembering that for the majority of human history, the ocean itself was mystery enough without worrying about what lay at its ultimate bottom. The trench was completely unknown to the sailors and navigators of the ancient world. They possessed no tools capable of measuring such depths. To them, the sea was already endless and formidable, a place of storms, capricious winds, and the lingering fear that monsters might dwell beneath. The notion of a trench deeper than the highest mountains would have been beyond comprehension. So, they filled the unknown with stories. They told tales of colossal serpents dragging ships into the deep, of whirlpools that could swallow entire fleets, and of gods and spirits who ruled over unseen kingdoms below the waves. The ocean was treated almost like a second sky, unfathomable and untouchable. Even in the modern era, the trench remains more of a legend than a reality for most people. We know of its existence, we can recite its statistics, we can watch videos or look at diagrams. But those numbers do not sink in easily. 11 kilometers down, pressure 1,100 times that of our air, a darkness so absolute that the only light comes from the creatures themselves. That gap between intellectual knowledge and true comprehension of the scale is part of why the trench still feels so enigmatic. It is not merely a fact to be memorized, it is an environment so extreme that it challenges our imagination. As we continue this journey, we will not rush. There is no need. The trench is not going anywhere. It has existed for millions of years, carved by the slow, grinding movement of Earth's tectonic plates, and it will remain long after we are gone. So, we can take our time to drift downward slowly, allowing our curiosity to unfold layer by layer. We will explore how the trench was first discovered, how it has been measured over the years, and what strange creatures inhabit its shadows. We will meet the submarines and robotic explorers that have dared to visit it. And we will look at the surprising connection between this abyss and the search for life beyond our own planet. We will even ask what it signifies that our own waste has reached the very bottom of the world. But for now, just notice the sensation of letting the surface slip away. Think back to the last time you stared out into the sea, whether from a sandy beach, a wooden pier, or perhaps through the window of an airplane. Did you ever wonder what lies beneath, how deep the water goes, or whether anyone has ever reached the very bottom? Tonight, that is exactly where we are heading. Not with flippers or climbing ropes, but with thought and story. Because in its own way, the Mariana Trench is as much a frontier as the edge of space. It serves as a reminder that even here on Earth, mysteries still surround us, waiting patiently in the dark. And so, with the waves quieting above us and the long descent just beginning, we can drift gently toward the edge of the map, the point where human knowledge once ended and imagination began. For much of human history, the ocean itself represented the edge of the known world. Before the advent of satellites, sound waves, and submarines, the sea was defined more by mystery than by knowledge. People could cross it, sail upon its surface, and harvest fish from its upper layers, but what lay beneath remained fundamentally hidden. The shoreline was a familiar boundary. Standing on the sand, you could see the waves, hear their crash, and feel their pull. But once a boat pushed out far enough that the land disappeared from view, the world changed. There were no landmarks to guide you, no roads to follow, just an expanse, so wide and restless that it often seemed infinite. It is no wonder that early map makers drew dragons and sea serpents in the blank spaces of the ocean, because when the known world ran out, imagination rushed in to fill the void. In many cultures, the sea was viewed not just as a body of water, but as a living presence. To the Polynesian navigators, it was a pathway of stars and swells that could guide them across thousands of miles. To the Norse, it was a realm ruled by gods and giants, a place where storms and monsters waited just beyond the horizon. In ancient Greece, the sea was the domain of Poseidon, a deity as unpredictable and powerful as the waves themselves. Across the globe, you find myths of creatures lurking beneath the waves, leviathans, krakens, spirits, and demons. These were not merely stories to pass the time, they were ways of explaining the unknown, giving shape to the profound unease people felt when staring out into waters that could not be measured or controlled. The truth is, even shallow depths were once beyond human reach. Sailors might lower ropes with weights tied to them to gauge the depth of the seafloor, but this was practical only in coastal waters. The deeper the ocean became, the more impossible the task. Ropes would drift in the currents. Weights would snag, and after a few hundred meters, even the most determined efforts became unreliable. Imagine standing on a deck, letting rope slip through your hands for hours, knowing it might never touch the bottom. For centuries, that was as close as anyone could come to probing the depths. The ocean floor might as well have been the surface of another planet. Still, curiosity persisted. Human beings are rarely content to leave a mystery unsolved for long. By the 16th and 17th centuries, when European explorers were crossing oceans to map new lands, they also began to wonder what lay beneath the waves they sailed upon. As maps of the continents filled in with detail, the seas remained vast blank spaces. "Here be dragons," one mapmaker famously scribbled in the margins. Whether the dragons were real or not didn't matter, the phrase captured the truth. Beyond the known edges, anything was possible. For the people who lived their lives on the sea, uncertainty wasn't just an abstract philosophical question, it was a daily reality. Fishermen wondered what shaped the currents that carried their boats. Traders wanted to know why storms appeared without warning. Sailors felt the ocean's moods firsthand, sometimes calm, sometimes violent, always larger than themselves. Every ripple on the surface hinted at secrets held below. And yet, for most of human history, those secrets remained untouched. The ocean was as much a ceiling as it was a floor. People looked out, not down. The Mariana Trench itself lay hidden through all of this. It sat in a remote corner of the Pacific, far from the main shipping routes of ancient trade, far from the coastal settlements where most human life concentrated. For thousands of years, it was simply unknown, the deepest part of the sea, invisible and silent, waiting in the dark while civilizations rose and fell above it. The fact that such a massive feature of our own planet could remain unseen for so long speaks volumes about just how unreachable the ocean depths were. When you think about the early attempts to measure the sea, it almost feels quaint now. Sailors would tie cannonballs to long ropes and lower them over the side, watching them vanish into the water. The rope uncoiled endlessly, and still no bottom was found. Sometimes the rope would stretch and break under its own weight. Other times it would stop, and they could record a number, though no one was sure if it had hit the true seafloor or just snagged on an underwater ridge or a passing current. Each attempt carried with it both frustration and wonder to think that beneath the boat there might be miles of open water, and below that, land no one could touch. These experiments slowly expanded human understanding, but the vast majority of the ocean floor remained unmapped. For people in those times, the sea's bottom was almost mythical. It was a place no one could reach, where unknown creatures might lurk, and where the earth itself might hold surprises. The idea of an abyss so deep it dwarfed mountains would have been unimaginable, and so the sea retained its place as the edge of the world both physically and mentally. What is fascinating is how the human mind fills in the gaps. Without direct knowledge, people invented explanations. Some believed the ocean had no bottom at all, that it was an endless void beneath the waves. Others thought it must be shallow everywhere, that the seafloor couldn't be that far away. Myths blended with guesses, guesses became beliefs, and beliefs shaped entire worldviews. The ocean was both feared and revered, a source of life and a threat of death. Its true nature remained hidden, and that made it powerful. Even into the 19th century, the deep sea was still largely a mystery. Ships sailed faster, trade grew larger, but the ocean depths resisted human understanding. It wasn't until new technologies arrived that the edge of the map began to shift downward. With stronger ropes, better weights, and eventually with the invention of sonar in the 20th century, people could finally begin to peel back the curtain. The Mariana Trench was revealed only gradually, a sound wave sent downward reflected back from a floor deeper than anyone had ever imagined. But for the centuries before that, the trench remained hidden under blank spaces on the map. And blank spaces have a power of their own. They invite stories, they invite fear, and they invite dreams. The edge of the map isn't just a physical boundary, it is a mental one too. Standing at that edge, humans have always looked outward and asked what might lie beyond. In the age before soundings and sonar, the sea itself was that question mark, and the Mariana Trench was its most secret answer, waiting in silence far below. And so, as we think about those blank maps, about sailors staring into horizons and wondering where the sea ended, it is worth remembering how recently the trench entered human knowledge at all. We may take it for granted now, a line of data on charts, a number to memorize. But for most of our history, the abyss beneath the Pacific was nothing more than a story untold. When people first tried to measure the ocean in a more serious way, they weren't just curious, they were practical. Mariners needed to know how deep waters were near coasts to avoid running aground. Naval commanders wanted to understand seafloor conditions for anchoring ships or planning routes. Fishermen wanted to know where certain catches were likely to gather. At first, these needs were met with the same simple tools that had been used for centuries: a length of rope and a heavy weight, often a piece of lead shaped to sink straight down. This method was called sounding. It worked well enough in shallow water, but when used in the open ocean, it was like trying to measure the height of the sky with a ladder. A rope could stretch for hundreds of meters, but beyond that, it became unmanageable. Imagine standing on the deck of a wooden ship with the wind tugging at the sails and the waves tossing you side to side as coils of rope unspool endlessly over the rail. The line drifts, the weight sways, and currents carry it at an angle rather than straight down. Sailors would wait, watching the rope vanish into darkness, uncertain if it would ever reach the bottom. Sometimes it never did, or if it did, no one could be sure whether it had touched rock or snagged on a hidden slope. These limitations didn't stop people from trying. In the late 18th and early 19th centuries, expeditions began to take a more systematic approach. Britain, with its growing naval power, had a strong interest in mapping and measuring the seas. The famous voyage of HMS Challenger in the 1870s is remembered today for its role in creating the field of oceanography, but even before Challenger, there were attempts to probe greater depths. Naval vessels would sometimes carry spools of hemp rope, thousands of meters long and heavy iron weights. When lowered into the ocean, the rope would be let out carefully, foot by foot, until resistance was felt. Sailors would mark the rope in intervals, usually with knots or pieces of cloth, so they could estimate how far down the weight had travelled. But hemp rope had problems. It swelled with water, stretched under its own weight, and broke under strain. A rope lowered several kilometers into the sea might lengthen so much that its measurements were meaningless. When the rope came back up, soaked and twisted, it might carry nothing more than a smear of mud. It was slow, exhausting work, and it was almost impossible to trust the results. By the middle of the 19th century, interest in the deep sea had grown for another reason: the telegraph. The idea of laying telegraph cables across the ocean floor meant engineers needed to know exactly how deep those floors were and what kind of terrain the cables would encounter. Suddenly, accurate measurements were not just matters of curiosity, but matters of global communication. A miscalculation could mean broken cables and failed connections. So, expeditions were launched with the specific goal of mapping the seabed more carefully. The United States Navy and the British Admiralty were among the first to take this challenge seriously. In 1852, the American ship Dolphin recorded what was then thought to be one of the deepest soundings, over 3,000 fathoms, which is more than 5,000 meters. Soon after, the British ship Cyclops measured even deeper waters. Each time the rope was let out farther, sailors were confronted with the staggering scale of the ocean. Depths were not just hundreds of meters, but thousands. Numbers that once seemed impossible began to appear in logbooks. And yet, even these attempts were shallow compared to the true abyss that no one yet suspected. A major breakthrough came with the HMS Challenger expedition of 1872 to 1876. This was not just a naval mission, but a scientific one designed to study the deep ocean systematically. The Challenger carried over 300 kilometers of rope, along with an array of dredges, nets, thermometers, and other instruments. It sailed nearly 70,000 nautical miles around the globe, taking hundreds of soundings along the way. For the first time, the ocean floor began to emerge not as an imagined void, but as a real landscape full of ridges, plains, and trenches. One of the most famous of these soundings was made in 1875 in the Western Pacific. The rope descended over 8,000 meters before it struck bottom. The site became known as Challenger Deep, though at the time no one realized it was the deepest point on Earth. For the scientists aboard, it was simply another astonishing number in a journey full of them. They recorded temperatures near freezing, samples of fine mud, and traces of life even from these crushing depths. The data they brought back transformed human understanding of the sea, filling volumes with observations that laid the foundation of modern oceanography. Still, the method was imperfect. Even Challenger's measurements were plagued with uncertainty. Currents pulled at the ropes, making them sag or drift. Sometimes the weights detached, giving false readings. A rope lowered to 8,000 meters might indicate a depth of 8,200 or 7,800, depending on conditions. Precision was elusive, and the abyss remained shadowy. Despite these monumental efforts, it wasn't until the 20th century, with the invention of sonar, that the ocean floor could be mapped with confidence. Instead of ropes and weights, scientists now used sound. They would send a pulse of sound downward and record how long it took to bounce back from the seafloor. The speed of sound in water was known, so the time delay could be converted into depth. This was faster, more reliable, and capable of covering large areas systematically. For the first time, the true shape of the seafloor came into view. Mountains, canyons, ridges, and trenches appeared in the data like a ghostly landscape unveiled. The Mariana Trench itself emerged from these sonar surveys as the deepest known feature. Its contours were mapped, its depth confirmed at over 11 kilometers. What rope and weight could only guess at, sonar revealed with clarity. The edge of the map had shifted, and in its place was a new frontier, the abyssal trench, the deepest scar on the planet. But it is worth pausing on those early attempts, those centuries when sailors leaned over wooden railings and fed out endless coils of rope into the sea. Their tools were simple, their results uncertain, but their efforts carried a spirit of persistence. They knew they might never see the bottom, and yet they tried. They lowered their weights, marked their ropes, and wrote down their numbers. Each sounding, whether right or wrong, was a step toward understanding. And even if they could not know it then, their efforts were the first links in a chain that would one day connect human curiosity to the floor of the deepest trench on Earth. Those first measurements were not just data. They were a reminder of scale, a confrontation with the immensity of our own planet. To stand on the deck of a ship and let ropes slip endlessly into the water was to feel small in a way that no mountain or desert could convey. The ocean was not just wide, but profoundly deep, deeper than anyone had imagined, and in that depth lay mysteries still untouched, waiting for the next generations to probe them more precisely. As soundings became more reliable and scientific voyages multiplied, the ocean floor slowly began to take form on the maps. No longer was it an unbroken flat plain hidden beneath the waves. Instead, evidence pointed to a landscape as varied as the land above, with peaks, valleys, ridges, and unexpected plunges. Among all these discoveries, one region in the Western Pacific began to stand out. Not because it was convenient to reach, but because the numbers that came back from it seemed almost impossible. In the late 19th century, after the Challenger expedition had already reported depths beyond 8,000 meters, other ships began to record even more dramatic soundings. Many of these came from naval and commercial expeditions traveling through the Pacific on routes that skirted the Philippines, Guam, and the Marianas. Time and again, when lines were lowered in certain areas east of the islands, the results suggested depths that surpassed anything measured elsewhere on Earth. At first, some suspected error. Ropes could still drift, weights could still detach, and sometimes results simply seemed too extreme to be credible. But as more ships passed through and more measurements were taken, a pattern began to emerge. By the early 20th century, scientists were convinced there was a great trench in the floor of the Pacific, an enormous scar formed by forces deep within the Earth itself. It stretched for over 1,500 miles, curving like a crescent parallel to the chain of volcanic islands that bore the same name. The Mariana Islands gave their name to the trench, honoring Queen Mariana of Austria, though the title of the trench was adopted much later than the islands themselves had been christened. The breakthrough that truly revealed the trench came with the advance of sonar. During the First World War, the need to detect submarines had driven rapid improvements in acoustic technology. By sending sound pulses into the sea and recording the echoes, navies could estimate the distance to a hidden submarine. Scientists quickly realized the same method could be applied to the seafloor. What had once required hours of lowering rope could now be done in seconds with much greater precision. Throughout the 1920s and 1930s, survey ships equipped with echo sounders began to cross the Pacific systematically. Each ping that traveled downward and returned carried with it a piece of the hidden landscape below. When these soundings were compiled, they revealed features that astonished scientists. The ocean was far from flat. Ranges of underwater mountains, now called mid-ocean ridges, stretched across entire basins. Deep plains extended for thousands of miles, and here in the Western Pacific, the seafloor plunged abruptly into a trench deeper than anywhere else on the planet. The Mariana Trench was no longer rumor or error. It was mapped, outlined, and confirmed as the deepest natural point on Earth. Its greatest depth, Challenger Deep, would not be fully measured until later. But by the middle of the 20th century, its place as the ultimate abyss was already recognized. It represented the limits of exploration, the farthest downward point that could be found without leaving the planet. For geologists, it was evidence of massive tectonic forces where one plate of Earth's crust was sliding beneath another in a process called subduction. For biologists, it was a potential habitat unlike any other, where life had adapted to crushing pressures, freezing cold, and eternal darkness. For everyone else, it was a reminder of mystery, a place so remote and extreme that it might as well have belonged to another world. To put its discovery into context, it helps to think of how human understanding of the Earth was changing at the same time. In the early 1900s, people were just beginning to grasp the idea of continental drift, The theory that continents moved across the surface of the Earth over millions of years. The oceans, once thought of as passive basins, were revealed to be active, dynamic, and deeply connected to the planet's geology. The discovery of the Mariana Trench fit into this shift perfectly. It was not just a hole in the ground, but a visible sign of tectonic power where crust was being recycled into the mantle. The planet, it turned out, was far more alive than anyone had imagined. But beyond geology, there was still the wonder of scale. When scientists announced that the trench reached nearly 11 kilometers down, people struggled to comprehend it. Numbers are abstract, but comparisons help. Imagine Mount Everest turned upside down and sunk into the Pacific. Its peak would still be more than a mile beneath the water's surface. Imagine a commercial airliner cruising at altitude. That is about the same height as the trench's depth. For those accustomed to thinking of mountains as the ultimate measure of size, this was a revelation. The Earth was just as extreme downward as it was upward. Of course, confirmation of the trench did not mean understanding it fully. In fact, it raised more questions than it answered. What creatures lived down there? How had they adapted? What were the temperatures, the currents, the chemistry of the water at those depths? Was it possible for humans ever to descend to such an extreme place? The trench was not just discovered, it was opened like a door, inviting questions that would drive decades of exploration. Even today, with advanced mapping and countless surveys, the trench holds an aura of mystery. Part of this comes from its inaccessibility. Only a handful of human beings have ever reached its bottom, and only for brief moments. Robotic probes and remotely operated vehicles visit more often, but the trench is vast, and each expedition samples only tiny parts of it. To say it has been discovered is not to say it has been understood. Much remains hidden in its folds, waiting patiently in the darkness. But to appreciate how remarkable that first discovery was, it helps to think of the perspective of the time. Imagine the moment when naval officers and scientists first saw the sonar readings, when they realized that the ocean floor fell away deeper than any mountain rose above the surface. Imagine how they must have felt, confronted with a number so large it defied intuition. The Earth had offered up one of its greatest secrets, not in the stars but beneath the sea. And just as explorers of earlier centuries had drawn dragons in the margins of their maps, scientists of the 20th century now filled in the blanks with soundings and charts, replacing myth with measurement. The discovery of the trench was not one event, but a gradual unveiling. It was the accumulation of countless soundings, each a small contribution to a larger picture. It was the work of sailors who lowered ropes into darkness, of engineers who built echo sounders, of scientists who compiled numbers into maps. No single person can be credited with the discovery. It was, like much of science, a collective achievement, but together their work transformed the unknown into the known, pulling the Mariana Trench from rumor into reality. And as soon as it was confirmed, attention turned naturally to the next question: what lay within? Knowing it existed was only the first step. To truly understand it, people would need to go deeper, not just with instruments, but with vessels strong enough to withstand the crushing pressure. The story of discovery was complete, but the story of exploration was only beginning. When the numbers first began to circulate, they didn't feel real. 11 kilometers, nearly 36,000 feet, a trench deeper than any other on Earth. To scientists who worked with measurements, the figures were astonishing. To the public, they were nearly incomprehensible. It's one thing to hear that the Mariana Trench is the deepest known point in the ocean. It's another thing entirely to try and imagine what that means in the scale of daily life. The truth is, the human mind struggles with extremes. We are comfortable with the size of things we can see and touch. A house, a tree, A hill, even a tall building in a city can be grasped by craning our necks upward, but thousands of meters of water pressing down into darkness that pushes far beyond instinct. To begin to imagine the scale, it helps to anchor it against things more familiar. Think first of Mount Everest, the tallest mountain above sea level, standing just over 8,800 meters high. If you could pick up Everest and drop it into the trench, its snow-capped peak would still vanish beneath more than 1.5 miles of seawater. The highest place on Earth would be swallowed with no trace visible at the surface. For people accustomed to thinking of mountains as the ultimate measure of vertical size, this comparison begins to give perspective. The trench is not just deep, it is deeper than the tallest landform is tall. Another way to think about it is by comparing it to the flight of airplanes. A typical commercial jet cruises at about 35,000 feet. Passengers look down on clouds, mountain ranges, and sometimes even the curvature of the Earth. That altitude feels impossibly high when you're strapped into a seat watching the world shrink below. Now imagine that instead of being above the clouds, you are beneath the ocean. The depth of the trench is roughly the same as the height of that flight. If you reverse the situation, taking an airliner and placing it on the seafloor of Challenger Deep, every passenger would be encased in black water with more ocean above them than air normally separates them from space. Skyscrapers, too, offer another perspective. The world's tallest building, the Burj Khalifa in Dubai, rises about 830 meters. An engineering marvel, it towers over the city, dwarfing other buildings around it. And yet, you could stack more than a dozen Burj Khalifas on top of one another and still not reach the surface if they were placed inside the trench. Even the most impressive human structures become insignificant compared to the depth of the abyss. Consider also the pressure at the surface. We live under one atmosphere of pressure, the weight of the air above us. It's so ordinary we don't notice it. But descend just 10 meters underwater and you add another atmosphere of pressure. Divers feel it in their ears, a squeeze that intensifies the deeper they go. At 30 or 40 meters, scuba divers require special training and equipment to avoid dangerous effects on the body. At 100 meters, few ever venture, and those who do must use highly specialized systems. By the time you descend to the bottom of the Mariana Trench, the pressure is over 1,000 atmospheres. It's equivalent to placing 50 jumbo jets on top of you. That unimaginable force would crush the strongest submarines of the early 20th century like tin cans. Even modern steel hulls require reinforcement and engineering far beyond ordinary design to survive. And yet, despite how inhospitable it sounds, life does exist there. Small, resilient creatures with bodies adapted to withstand the pressure make their homes in that crushing environment. Some have flexible membranes instead of rigid structures, allowing them to bend rather than break. Others rely on unique chemical systems to keep their cells stable. For them, the trench is not extreme, it is simply home. But for humans trying to comprehend it, the sheer numbers stretch the imagination. It helps to think about time. Imagine lowering a weight into the trench on a rope, as sailors once did. Even if it sank at 2 meters per second faster than most heavy objects realistically descend in water, it would take an hour and a half to reach the bottom. That's 90 minutes of falling straight down through layer after layer of darkness with no pause. By the time the weight touched bottom, the ship above might have drifted miles on the surface, pulled by wind and current while the rope stretched far behind. That kind of scale is not just physical but temporal. It takes time to fall that far. The trench is not only deep, it is long in duration, so deep that the act of reaching its floor feels like a journey in itself. And then there is temperature. The surface of the Pacific can be warm, inviting, sunlit, but descend into the abyss and temperatures drop until they hover near freezing. Just above the seafloor, the water is only a few degrees above zero. It's not frozen because of the immense pressure, but it is cold enough to sap the energy of anything unprepared. The contrast between the tropical surface and the icy depths only adds to the sense of scale. It's not just distance, it's a complete transformation of environment. To make the size more tangible, scientists sometimes compare the trench to canyons on land. The Grand Canyon, carved by the Colorado River over millions of years, is about 1.6 kilometers deep at its maximum. Standing on the rim and looking down, visitors often feel overwhelmed by the vastness of the chasm. But the Mariana Trench is nearly 7 times deeper. Imagine standing on the floor of the Grand Canyon and looking up at walls so high you could stack 6 more canyons above them before reaching daylight. That is the proportion we're dealing with. Even with these comparisons, the trench retains an element of incomprehensibility. The numbers are so large they resist easy visualization. That difficulty in imagining is part of why the trench feels so mysterious. It exists at the edge of what our minds can comfortably picture, and perhaps that is fitting. The deepest place on Earth should not be easily grasped. It should feel overwhelming, humbling, even a little unreal. Yet, the scale is not just about numbers, it's about what those numbers mean for exploration. To reach the bottom requires equipment strong enough to endure pressures far beyond ordinary design. It requires vessels that can function in the dark, in the cold, with no possibility of rescue if something goes wrong. It requires months of planning, years of engineering, and resources that only a handful of institutions or individuals can muster. That is why so few expeditions have ever reached Challenger Deep. The scale of the trench is not only a matter of size, it is a barrier to entry, a reminder of the limits of human technology. And yet, as much as the trench dwarfs our imagination, it also inspires it. To know that such a place exists on our own planet, hidden beneath the Pacific, gives perspective on our position in the universe. We often look outward to space and imagine other worlds as mysterious and unreachable. But here, beneath the waves, lies a place just as alien, just as extreme, and in some ways even less explored. It is possible that we know more about the surface of Mars than we do about the floor of the Mariana Trench. That comparison alone speaks to its scale, not just in physical terms, but in terms of knowledge. The trench is not a single point. It is a vast system stretching more than 1,000 miles across the Pacific floor. Within it are valleys, ridges, and slopes, each with their own conditions. Challenger. Deep may be the lowest known point, but it is only one feature within a larger scar. To map it all would require countless surveys, each crossing back and forth with sonar, building a picture piece by piece. Even with satellites that can estimate depth by measuring the way gravity affects the surface of the sea, the resolution is limited. The trench remains partly a mystery because of its scale. It is too large to be fully grasped at once, too deep to be visited easily, too remote to be studied continuously. When explorers speak of standing at the rim of the trench, they describe a feeling of awe, as if peering into a bottomless void. The ocean simply falls away, a slope that drops into blackness with no visible end. That impression of infinity is another measure of scale, not of numbers, but of perception. It feels endless, even though we know it is not. The human mind interprets that kind of plunge as limitless because it stretches far beyond everyday experience. And so the scale of the Mariana Trench is both a scientific fact and a psychological experience. It is 11 kilometers deep, 1,500 miles long, and home to pressures 1,000 times greater than the surface. But it is also a symbol of the vastness of our planet. A reminder that there are places on Earth that remain as challenging and mysterious as the stars above. The trench forces us to think bigger, to imagine beyond our usual limits, to confront the immensity that lies hidden beneath something as ordinary seeming as water. From here, with the enormity of that depth in mind, it becomes easier to understand why pressure plays such a defining role in what happens there. For life, for exploration, for geology, the crushing weight of the ocean shapes everything in the abyss. Once you begin to picture the depth of the Mariana Trench, the next thought that naturally follows is what that much water actually does. 11 kilometers of ocean stacked above you isn't just distance, it's weight. Every drop of water carries mass. And when you pile billions upon billions of drops into a vertical column more than 6 times deeper than the Grand Canyon, that mass adds up to something nearly impossible to imagine. It becomes pressure. And pressure changes everything. On the surface, pressure is so ordinary that we rarely notice it. Right now, whether you're indoors or outside, sitting or lying down, the air above you presses down with the weight of 1 atmosphere. That's about 14 pounds for every square inch of your body. Multiply that across your skin, and it comes out to several tons. The only reason you don't feel crushed is that your body pushes back from the inside with equal force. You are, in a sense, adapted to live comfortably under a blanket of air you can't see. But even the smallest change in that balance becomes noticeable. If you've flown in an airplane, you've probably felt your ears pop as the pressure shifted in the cabin. If you've swam in a pool, you've felt the squeeze in your sinuses after diving only a few feet down. Those sensations are tiny glimpses of what pressure really means. Now extend that thought. Every 10 meters you descend into the ocean adds another atmosphere of pressure. At 10 meters, you're at 2 atmospheres. At 20 meters, 3. At 30, 4. For scuba divers, those numbers quickly become serious. Breathing compressed air under such conditions alters the balance of gases in the body, and beyond certain limits, it becomes dangerous. Specialized training and equipment are needed for dives even a fraction of a kilometer deep. Yet, the trench plunges to nearly 11 kilometers. That means that at the bottom, the pressure is over 1,000 atmospheres. To put it another way, it is more than 1,000 times what you're experiencing at this moment. Scientists sometimes compare this to elephants or jumbo jets sitting on top of you because such comparisons at least give a hint of the scale. Imagine trying to withstand the weight of 50 fully loaded aircraft pressing down on a single point. Steel beams would crumple, concrete would fracture. Submarines built for ordinary naval use would collapse instantly. The ocean at those depths is not passive. It is actively crushing, pressing inward with unimaginable force. Anything that descends into the trench must be designed entirely around the goal of resisting or adapting to that pressure. And yet, life exists there. This is perhaps the most remarkable fact. For humans, the trench represents a hostile environment requiring advanced technology just to survive for a few hours. For small organisms, it is simply home. Over millions of years, evolution has produced creatures whose very structures are built to function under those conditions. Instead of rigid shells or bones that would shatter, many deep-sea species have flexible bodies. Their cell membranes are reinforced with special molecules that prevent them from collapsing under the squeeze. Their proteins, the tiny machines that keep cells alive, are stabilized by unique chemical adaptations that stop them from unfolding under stress. In some cases, entire species are known only from the trench, perfectly suited to its crushing embrace and unable to survive in shallower waters where pressure is lower. The trench shows that life isn't fragile in the way we sometimes think. It is adaptable. It finds ways to persist, even where forces seem overwhelming. For biologists, this is a profound insight. If life can thrive under more than 1,000 atmospheres of pressure, perhaps it can also survive in the icy oceans beneath the crust of Europa, one of Jupiter's moons, or Enceladus, a moon of Saturn. The trench becomes a kind of model, a natural laboratory showing how extreme conditions need not mean lifelessness. But for humans, pressure remains a barrier. When engineers began designing vessels to reach the trench, they had to consider not only the strength of the hull, but the behavior of every component. Wires, bolts, seals, even the glass in viewing ports had to be built to withstand forces far beyond ordinary design. In 1960, when the bathyscaphe Trieste made its historic descent to Challenger Deep, its spherical crew cabin was made of steel several inches thick, carefully shaped so that pressure would be distributed evenly across the surface. Even so, as it sank, the explorers inside heard cracks and groans as the metal adjusted to the squeeze. At one point, the outer window cracked under the strain, though the inner barrier held. They remained safe, but the sound was a reminder of just how close the line between success and disaster can be when facing the weight of an entire ocean. Modern unmanned submersibles face the same challenges. Every electronic system must be shielded, every joint must be sealed. Batteries must be designed not to rupture under pressure. Even the simplest experiment, such as sending down a camera, requires protective casing strong enough to keep the crushing water out. And when objects not built for the trench are taken down, the results are dramatic. Styrofoam cups sent to the bottom emerge shrunk to a fraction of their original size, compressed by the weight of the sea. It is a vivid demonstration of how absolute the pressure really is. Even rock and geology respond differently under such conditions. Sediments at the bottom of the trench are compacted into dense layers. The immense pressure contributes to the way tectonic plates move and interact. In fact, the trench exists because of that pressure in the first place, formed where the Pacific Plate is forced beneath the smaller Mariana Plate in a process that has shaped earthquakes, volcanoes, and island chains. The pressure is not just a consequence of the trench. It is part of the mechanism that created it. For anyone imagining what it would feel like to be down there, the answer is simple. Without protection, it would be instant death. A human body built for 1 atmosphere cannot endure even a small fraction of the conditions at the bottom of the trench. Lungs would collapse. Blood would be forced into unnatural states. Cells themselves would be crushed. This is why stories of free divers plunging hundreds of meters, impressive though they are, can never be extended further. There is a hard physical boundary. The trench is not a place where humans can ever belong naturally. It is instead a realm we can only visit briefly, encased in steel and technology, separated from direct contact by layers of engineering. Yet, despite how hostile it is, the pressure of the trench is also strangely reassuring. It demonstrates the raw, undeniable power of nature. In a world where human influence reaches into nearly every corner of the environment, the trench remains a place beyond our direct control. It reminds us that there are still limits, still boundaries that demand respect. For explorers, that pressure is both a challenge and a warning. It is the reason why so few have descended into the abyss, but it is also the reason why those who do describe the experience with awe. And even knowing the dangers, curiosity persists. People want to see what exists in that dark, pressurized world. They want to understand how life adapts, how geology shifts, how ecosystems function under such conditions. They want to test the boundaries of technology to prove that even in the face of 1,000 atmospheres, exploration can continue. Pressure is not only an obstacle, it is part of the allure. It is what makes the trench extreme, mysterious, and worth studying. When you consider the scale of that weight pressing inward from all sides, you might expect silence. And in many ways, silence does dominate. But pressure also affects sound. At great depths, sound waves travel differently, moving faster and farther than at the surface. In the trench, the weight of water compresses everything, even the medium through which sound moves. What results is an environment where hearing becomes as important as seeing, because light cannot reach but sound can. Scientists who listen to the trench hear strange clicks, groans and rumbles carried vast distances through the pressurized water. Some of these sounds come from earthquakes, others from distant storms, still others from creatures adapted to the abyss. Pressure not only crushes, it also carries, transmitting information in ways we're only beginning to study. To understand the trench, then, is to understand pressure. It is the defining characteristic of the abyss. It shapes the environment, the creatures, the technology, and the experience of exploration. It is what makes the trench unique, what separates it from the shallower seas that most of us know. The trench is not just deep water, it is a world redefined by pressure, a place where everything is compressed, compacted, and transformed by the weight of the ocean above. As soon as you picture the depth and the pressure of the Mariana Trench, another fact naturally follows. Light cannot reach there. Not the faintest trace of sunlight makes it to the bottom. Even before you approach the trench itself, long before, at a few hundred meters beneath the surface, the sun has already disappeared. At around 200 meters down, you enter what scientists call the twilight zone, where light is dim and blue, shapes blur, colors fade, and vision becomes unreliable. Beyond that depth, sunlight is gone entirely. Everything deeper exists in perpetual night. The trench, lying more than 10 kilometers beneath the surface, has been in darkness for millions of years, and it will remain so long after us. Darkness of this kind is hard to imagine because human beings live entirely in the light. Even at night we have stars, street lamps, screens, or the glow of the moon. True, total darkness is rare. Our eyes are not built for it. Spend a few moments in a darkened room and your pupils adjust, reaching for whatever faint light they can find. But in the trench, there is nothing for them to adjust to. There is no light from above, no glow from the moon, no hint of dawn or dusk. It is a blackness more complete than anywhere on the surface of the earth. And yet, strangely, the darkness does not mean emptiness. Life still thrives there, but it has had to adapt in remarkable ways. Some species have dispensed with eyes entirely, their ancestors having lost them over generations because they offered no advantage in a world without light. Others, paradoxically, have developed enormous eyes capable of catching even the faintest glimmers, not from the sun but from bioluminescence, the living light produced by creatures themselves. In this darkness, the only illumination comes from life. It's as if the trench has its own constellations, not above but within, made of tiny organisms glowing blue, green, or red for brief moments before vanishing back into black. Bioluminescence is one of the most extraordinary adaptations to darkness. Chemical reactions within cells produce flashes of light used for communication, hunting, or camouflage. Some creatures emit a glow to lure prey closer, others flash to startle predators, still others use it to recognize mates in the vast dark expanse. The trench is filled with organisms that glow in strange patterns, creating a landscape of moving sparks invisible to human eyes unless captured by special cameras. For them, light is not something that streams from the sky. It is a language written in flickers and pulses, essential for survival. But not all creatures rely on light. Many have adapted in silence and blindness, using senses other than sight to navigate. Some detect vibrations in the water, sensing movement even in the absence of vision. Others rely on chemical cues, essentially tasting their surroundings as they drift or crawl along the seafloor. To us, this may seem alien, but in the trench, it is simply the way of life. When vision is useless, evolution leans on other senses. For humans trying to explore, the darkness is another formidable barrier. Cameras sent into the trench must carry their own lights, powerful beams that can pierce a small bubble of water but fade quickly beyond it. In photographs and footage, the surrounding black seems absolute, swallowing light almost immediately. What we see in those images is not the trench as it usually appears, but a momentarily illuminated stage lit by artificial lamps. Without them, the environment is invisible. Explorers sitting inside submersibles describe looking out of portholes and seeing nothing but their own reflections unless their vessel's lamps are switched on. It is disorienting, a reminder that the abyss does not reveal itself willingly. This eternal night also affects the rhythms of life. On the surface, most organisms follow cycles of day and night, activity and rest. Plants open and close with the sun. Animals feed and sleep according to the rising and setting of light. In the trench, those cues are gone. Time does not pass in the same way. Organisms may follow other rhythms, perhaps linked to the slow drift of nutrients sinking from above or to internal cycles built into their biology. But the daylight cycle, the most familiar of all patterns on the surface, is absent. It is an alien world, not because it lies on another planet, but because it operates outside the rules we take for granted. Darkness also plays tricks on our imagination. For centuries, people feared what might lurk in unseen places. Myths of sea monsters often drew their power from the idea of creatures hidden in black depths. Even today, part of what makes the trench feel mysterious is not just its depth, but its invisibility. When you can't see, your mind fills the gap. The unknown becomes a canvas for fear and wonder alike. Scientists approach with instruments, but ordinary people approach with stories. Both are ways of trying to make sense of what cannot be seen. The trench is a reminder that light is not a universal condition. On Earth, we think of the sun as everywhere, its light touching all things. But the truth is, most of the planet is dark. The oceans cover over 70% of the globe, and most of that water lies below the reach of sunlight. The trench is simply the deepest part of this dark majority. In a sense, the surface where we live is the exception, a thin film of light clinging to the top of a vast, shadowed world. When scientists first began sending cameras into the trench, many expected to find barren emptiness. Surely nothing could live in such a cold, pressurized night. But what they discovered instead were ecosystems alive with strange creatures. Amphipods, translucent shrimp-like animals, crawl along the seafloor. Snailfish, pale and ghostly, swim in slow arcs. Microbes thrive in sediments, feeding on chemicals instead of sunlight. Each of these creatures is a testament to life's ability to flourish, even in darkness. What seems inhospitable to us is perfectly normal to them. The eternal night is not an obstacle. It is a condition of life, and life has embraced it fully. There is also something humbling about thinking of Earth in this way. We often imagine ourselves as living on a planet of light with a glowing sun overhead and a moon reflecting its beams by night. But really, we live on an ocean planet, and most of it is hidden from sight. The trench is a reminder of that hidden majority. To study it is to confront the reality that light is not the rule, but the exception, and that much of the biosphere thrives in conditions we might call invisible. For explorers, darkness is both a challenge and a wonder. It makes the trench difficult to study, but it also gives it a unique character. Unlike space, which offers distant starlight, the abyss offers no background glow. It is absolute. Cameras reveal only what is illuminated directly in front of them. Beyond that, the black is impenetrable. To sit in a submersible at the bottom of the trench is to sit inside a bubble of light surrounded by infinite shadow. Some explorers describe the experience as calming, others as unsettling, but all agree it is unlike anything on the surface. In a place where light has vanished, sound becomes the only language left. It might seem strange to imagine the ocean as anything other than silent, especially in its deepest parts. From the surface, standing on a quiet beach or drifting on a calm lake, the water seems hushed, a place of gentle waves and soft breezes. But beneath the surface, sound travels differently. And in the abyss of the Mariana Trench, it becomes one of the only ways to perceive what is happening. Where darkness hides everything from view, sound slips through with surprising clarity. Unlike light, which is quickly swallowed by water, sound moves faster and farther in the ocean than it does in air. That is why whales can communicate across vast distances, why naval sonar can detect submarines miles away, and why even the faintest noises from the surface sometimes reach unimaginable depths. In the trench, the pressure and temperature of the water alter the way sound travels, bending and guiding it through layers like invisible corridors. Scientists call this the sofa channel, a deep sound channel where noises can be carried for thousands of kilometers. In effect, the ocean is wired for listening. So when microphones called hydrophones were lowered into the trench for the first time, scientists did not find silence. They found a soundscape, strange and varied, filled with signals, both natural and artificial. Some of the noises were familiar: the rumbles of distant earthquakes, the echoes of underwater landslides, the rhythmic calls of whales far above. Others were more mysterious, unidentified clicks, groans, and pulses with no clear origin. In the deep, sound carries across enormous distances, so a noise made hundreds or even thousands of miles away might arrive faint but distinct at the bottom of the trench. Even storms on the surface can be heard. Rain falling on the Pacific creates a hiss that filters down, audible far below. Thunderclaps roll like muffled drums. Waves crashing in distant hurricanes send vibrations deep into the ocean's body. For a listener sitting at the bottom of Challenger Deep, the surface is not silent at all. It is alive with distant energy, translated into sound and carried downward like a memory of the storm. Then there are the sounds of life. Many deep-sea creatures are not silent. Some produce clicks or pulses to communicate, others to hunt. Shrimp can snap their claws to create sharp bursts. Certain fish drum against their swim bladders to create vibrations. Even in the trench, life announces itself, though the calls may be faint or difficult to interpret. For animals in complete darkness, sound is often as essential as vision is to us. It tells them where others are, what is moving, whether danger is near or food is approaching. Each click and rumble becomes part of a vast unseen conversation. Humans listening in for the first time were surprised by just how busy it seemed. They expected a void, perhaps occasional groans of the earth itself, but instead they heard variety. It was not silence. It was a different kind of presence, one that revealed how active the ocean really is. The trench may be far from sight, but it is not disconnected from the rest of the world. Every quake, every storm, every passing creature leaves traces in its waters. Of course, not all of the sounds are natural. Ships above with their propellers and engines send vibrations down through the sea. Sonar pulses from naval vessels designed to detect submarines sometimes echo in hydrophone recordings. Even human industry thousands of meters above can intrude upon the deep. The trench, though remote, is not immune to the influence of civilization. Scientists studying the recordings often note how much of what they hear can be traced back to us. A reminder that even the deepest abyss is connected to human activity. And then there are the unidentified sounds, those that resist explanation. Strange whistles, groans, and tones that do not match known species or natural phenomena. Some of these mysteries are eventually solved. A noise once thought mysterious turned out to be the call of a particular whale species. Another, the echo of shifting icebergs thousands of miles away. But some remain unexplained. odd signatures that continue to spark curiosity. For many, these unknown sounds are the most fascinating part. They remind us that the deep ocean still holds secrets, not only in its physical darkness, but in its acoustic world as well. One of the most remarkable aspects of listening to the trench is how it collapses distance. A hydrophone lowered into Challenger Deep may record sounds originating half an ocean away. An earthquake near Japan, a storm near Hawaii, a whale call from hundreds of miles north, all can arrive in the same recording, overlapping in strange harmony. The abyss is not isolated, but connected through sound. In a sense, the trench is an ear pressed against the body of the earth, receiving whispers from across the globe. Explorers who have descended in submersibles often describe how different sound feels in the deep. The vessels are sealed, so what they hear directly is muted, but the groans of the hull as it adjusts to pressure can be startling. Every creak is magnified by the knowledge of what surrounds them, a crushing force that allows no margin for error. Outside the sub, silence reigns to the human ear. But through instruments, the water comes alive with signals. For the people inside, it is like being cut off from one sense and given another, a reminder that perception itself is relative. The study of sound in the trench is still young, but it has already revealed a surprising amount. It shows that even at the deepest point on Earth, the ocean is not cut off. It is part of a global system of motion and energy, its waters vibrating with the memory of storms, quakes, animals, and human activity. Silence in the trench is not absence. It is filled with echoes. When people imagine alien life, they often picture distant planets with harsh landscapes, strange atmospheres, and bizarre creatures that look nothing like anything on Earth. Yet, if you wanted to see something alien without ever leaving this planet, you would only need to look into the deep ocean. The trench, with its darkness, pressure, and silence, has produced living forms so unusual that they feel like they belong to another world entirely. Scientists sometimes say that studying the deep sea is like studying space, not only because both are extreme frontiers, but because the creatures found there challenge our understanding of what life can be. The most obvious difference between trench life and the creatures we know on the surface is appearance. Without sunlight, there is no need for colors the way we're used to them. Green leaves, blue feathers, golden fur. All of these are tied to light. In the abyss, colors fade away. Many creatures are transparent, their bodies like glass, making them nearly invisible. Others are ghostly white or pale pink with skin that reflects nothing because there is nothing to reflect. And then there are those that glow. Bioluminescence is so common in the deep that it could be called the trench's equivalent of sunlight. Flashes of green, blue, or red light pulse from the bodies of fish, jellyfish, and tiny plankton. Some produce steady glows, others rapid bursts, still others twinkling patterns. To the human eye, it looks like drifting stars scattered across black water. One of the strangest examples is the anglerfish, famous for the glowing lure that hangs from its head. In the eternal night, the lure is a hunting tool. Small fish and crustaceans are drawn to the light, mistaking it for food or company, only to be swallowed by the waiting predator. The anglerfish itself looks almost monstrous, with a huge mouthful of needle-like teeth and a body adapted for swallowing prey nearly as large as itself. To us it looks frightening, but in the trench it is simply efficient, a design honed by evolution to survive where food is scarce and opportunities fleeting. Other creatures use light not for hunting but for disguise. Some emit a glow from their undersides that matches the faint light filtering from above, a trick called counter-illumination. To predators looking up from below, the glowing belly blends with the dim light, making the creature invisible. Still others use light to communicate, sending flashes to attract mates or warn rivals. For them, light is not beauty, but language. It is survival in code, written across bodies that drift through the black. Beyond light, many trench creatures seem alien because of their proportions. In the absence of gravity's usual influence, bodies can take on shapes that would seem impractical on land. Giant squid with eyes the size of dinner plates peer into the darkness, their tentacles reaching extraordinary lengths. Gulper eels open mouths so large they seem out of proportion to their slender bodies, capable of engulfing prey much larger than themselves. Blobfish, which have become icons of deep-sea strangeness, appear gelatinous and distorted when brought to the surface because their bodies are adapted to balance against crushing pressure, not the relative emptiness of shallow water. Size itself takes on extremes. Some deep-sea creatures are miniature, adapted to survive on the tiniest scraps of food. Others grow to enormous proportions, like the colossal squid or the giant amphipods discovered in trenches, far larger than their shallow water relatives. This phenomenon, sometimes called deep-sea gigantism, is still not fully understood. Some scientists think it relates to slower metabolisms in the cold, high-pressure environment. Others suspect it is an adaptation to scarcity, with larger bodies allowing more efficient energy use. Whatever the reason, the result is creatures that seem exaggerated, stretched beyond normal limits, as if designed in the imagination of someone inventing alien species. And then there are the microbes, the invisible majority of life in the trench. In sediments on the seafloor, in the pores of rocks, and in the water itself, microbial communities thrive. They do not need sunlight or photosynthesis. Instead, they rely on chemosynthesis, using chemicals like methane, hydrogen, or sulfur to fuel their metabolism. Some are extremophiles, organisms adapted to conditions of extreme temperature, pressure, or acidity. These microbes are especially fascinating because they demonstrate that life does not require the conditions we take for granted. If they can thrive in the crushing cold dark of the trench, why not in the oceans beneath the ice of Europa or in hydrothermal vents on other planets? To astrobiologists, the trench is not just a curiosity, it is a blueprint, evidence that life can emerge and persist under conditions once thought impossible. For most people, seeing images of trench creatures is enough to provoke both wonder and unease. The translucent bodies, the gaping jaws, the glowing patterns, they look unlike anything in daily experience. But to see them as monstrous is to see them through the wrong lens. To them, we are the aliens, creatures who require sunlight, air, and fragile balances to live. In their world, they are perfectly adapted. Their strangeness is only a reflection of our unfamiliarity. Explorers who have seen these creatures firsthand often describe the experience as surreal. Sitting in a submersible, shining lights into the dark, they watch as unfamiliar forms drift into view. Some move slowly, conserving energy. Others dart quickly, seizing the chance for a meal. A shrimp-like creature may float past, glowing faintly. A fish with transparent skin might hover just outside the beam. For the humans inside, it feels like looking at animals from another planet. But the realization follows quickly. This is our planet. These are Earth's aliens hiding in plain sight, unknown to us simply because they live where we cannot go. The diversity is immense. Scientists estimate that only a fraction of deep-sea species have been identified. Each expedition tends to bring back new discoveries, sometimes entire new families of organisms. In recent years, robotic submersibles have filmed strange gelatinous blobs, spiral-shaped siphonophores stretching dozens of meters, and jellyfish that pulse with light like living lanterns. Each find adds to the sense that the trench is not just a hole in the ground, but an ecosystem teeming with complexity we have barely begun to understand. Food in the trench is scarce, and this scarcity shapes the behavior of its inhabitants. Most of the energy that sustains life there comes from marine snow, a gentle rain of organic particles drifting down from the surface. Dead plankton, bits of algae, fragments of larger creatures all fall slowly through the water, sometimes taking weeks to reach the bottom. For trench creatures, this snow is precious. They sift it, capture it, and compete for it. Some animals are scavengers, rushing to consume the carcasses of whales or fish that sink to the depths. Others feed on bacteria that themselves consume the organic material. The entire ecosystem is built on the faint trickle of energy from above, a slow, sparse economy where nothing is wasted. And yet, despite these harsh conditions, the trench harbours surprising abundance. In sediments, microbial populations number in the millions per cubic centimetre. Amphipods swarm around baits lowered by researchers, arriving quickly, even from the shadows. Fish patrol the slopes, adapted to pressures that would crush surface species instantly. This abundance speaks to the resilience of life. Even in a place where light never shines, where food arrives only in fragments, where pressure is overwhelming, life finds ways not only to exist, but to flourish. For humans, the trench provides more than scientific data. It offers perspective. To look at its creatures is to realize that our definition of normal life is narrow. We think of grass, birds, mammals, and trees as the standard. But in truth, most of the planet's biosphere is very different. The trench's inhabitants remind us that life is not limited by our expectations. It is flexible, adaptable, and endlessly inventive. In that sense, studying them is not just about cataloguing species, it is about broadening our understanding of what life itself means. And when you think about that, about glowing fish, transparent shrimp, microbes that eat chemicals instead of sunlight, and creatures that could be mistaken for designs from science fiction, the name alien life doesn't feel like an exaggeration. They are alien to us, but not to the Earth. They have been here all along, hidden in darkness, thriving in pressure, waiting for us to look closely enough to notice. Once you know such creatures exist, the next question is how humans ever managed to reach them, to see them in person, to descend into that black, pressurized world. By the middle of the 20th century, the Mariana Trench had shifted from rumor to fact. Sonar surveys confirmed its depth. Expeditions had mapped its curves and slopes. Scientists knew that Challenger Deep was the deepest known point on the planet. But knowing was not enough. Curiosity has a way of pressing further, asking not just how deep, but what it looks like, what it feels like, and whether it can be reached by people. For centuries, the trench had been inaccessible. By the 1950s, technology had advanced enough that an attempt no longer seemed impossible. The vessel chosen for this unprecedented journey was called Trieste, a bathyscaphe designed in Switzerland and later purchased by the United States Navy. The word bathyscaphe itself combines the Greek words for deep and ship. Trieste looked nothing like the sleek submarines that people might picture. Instead, it resembled a floating platform with a large white gasoline-filled float on top and a heavy steel sphere slung underneath. The float provided buoyancy, while the sphere was where the crew would sit. That sphere, just a few meters wide, was built of steel over 12 centimeters thick, engineered to withstand the crushing pressures of the deep. Inside the sphere, there was room for only 2 people. In January of 1960, those 2 were Jacques Piccard, a Swiss oceanographer and engineer whose father had helped design the craft, and Don Walsh, a US Navy lieutenant. Together, they prepared to attempt what no one had ever done, descend all the way to Challenger Deep, nearly 11 kilometers below the surface. The dive began near Guam on the morning of January 23, 1960. Trieste was towed out to sea and made ready. The float above the crew sphere contained gasoline, which, being lighter than water, provided the necessary buoyancy. To descend, the bathyscaphe carried tons of iron pellets as ballast. By releasing or holding these pellets, the crew could control their descent or ascent. It was a simple but effective system, relying on gravity and buoyancy rather than propellers or engines. At the start of the dive, Pickard and Walsh climbed into the cramped steel sphere through a narrow hatch. Once sealed inside, they had only a few small viewports of thick glass to look through. The interior was barely large enough to sit in. There was little room to move, and the air was humid and stale. They carried a limited supply of oxygen and carbon dioxide scrubbers to keep the atmosphere breathable. Communication with the surface was maintained by radio, though signal quality was poor at such depths. With final checks complete, they began their descent. The first part of the journey was surprisingly fast. As ballast weights pulled them downward, they sank through the upper ocean layers. Light quickly faded, replaced by dim blue, then black. Through the windows, little could be seen beyond occasional drifting particles. Minutes stretched into hours. Pressure outside the sphere increased relentlessly, though inside they remained safe, encased in their tiny bubble of steel. The sounds of the dive were mostly mechanical. The creaking of the hull as it adjusted, the crackle of static over the radio, the faint hum of instruments. At around 9,000 meters, something alarming happened. One of the outer plexiglass viewports cracked under the immense pressure. A loud bang echoed inside the sphere, startling both men. But the inner glass and the steel sphere held. They continued, knowing that the margin for error was thin. In an environment where pressure exceeded 1,000 atmospheres, even the smallest failure could be fatal. Yet they pressed on. The descent took nearly 5 hours. Imagine sitting in a steel ball knowing that kilometers of water are piling above you, the weight increasing every second. The darkness outside is absolute. The journey is not like falling, but like sinking endlessly, slowly deeper and deeper into an invisible world. At last, the depth gauge indicated nearly 10,900 meters. They had arrived at Challenger Deep. The bottom of the trench was not what many had expected. Through the windows, Pickard and Walsh saw a flat, muddy seafloor covered with fine sediment. The water around them was surprisingly clear, though illuminated only by the vessel's lights. And then, most astonishing of all, they reported seeing life. Small fish resembling flatfish or sole moved slowly along the bottom. Their presence proved that complex organisms could survive even in the crushing pressure of the deepest ocean. For scientists of the time, this was revolutionary. It challenged assumptions that life could not exist at such depths. Pickard later described the seafloor as a waste of beige mud as far as the eye could see. Walsh recalled that it was featureless but not lifeless. The two men had only about 20 minutes at the bottom. Their instruments recorded the conditions. They took in the view, limited as it was, and then they released ballast to begin their ascent. The journey upward was faster, taking about 3.5 hours. By releasing iron pellets, the bathyscaphe became lighter and floated toward the surface. At last, after nearly 9 hours underwater, Trieste surfaced. Pickard and Walsh emerged, cramped, tired, but alive, having reached a place no human had ever been before, and proving it was possible. The dive of Trieste remains one of the great achievements of exploration. In some ways, it was the underwater equivalent of the first moon landing. Just as astronauts stepped onto another world, Pickard and Walsh descended into Earth's deepest abyss. Their dive showed that technology could overcome the immense pressures of the trench, at least for a short time. It also showed that life persisted even in the most extreme environments. And yet, despite its success, the dive was not repeated by humans for decades. The technical challenges and costs were immense. Trieste herself was retired, preserved as a piece of history. The trench returned to silence. visited only by unmanned probes until the next generation of explorers would arrive. For those two men, the memory of the descent remained vivid. Walsh would later describe it as both terrifying and awe-inspiring, a journey into an alien world. Picard saw it as a triumph of human curiosity and engineering. Together, they had shown that the abyss could be reached. When people speak of the Mariana Trench today, the dive of Trieste is always remembered. It was the first time human beings looked directly at Challenger Deep. The first time the deepest point on Earth was not just measured, but experienced. That moment bridged centuries of speculation and centuries of myth. The trench was no longer unreachable. It was real, visited, and seen with human eyes. The name Challenger Deep carries with it both history and mystery. It is not just a spot on a map, not just a number on a depth gauge. It is the symbol of the ocean's ultimate extreme, the deepest known point on Earth. The name itself comes from HMS Challenger, the British research vessel that sailed in the 1870s on a global expedition, the first great scientific survey of the deep sea. That voyage gave birth to modern oceanography, and when its soundings suggested an unusually deep place in the Western Pacific, the connection became permanent. Decades later, as more precise measurements confirmed the spot, it was officially given the name Challenger Deep, honoring the ship that first revealed it. Challenger Deep is not a single hole or pit, but a small region at the southern end of the Mariana Trench. Within this region, there are 3 known basins, each with slightly different depths, spread across a few tens of kilometers. Which of these is truly deepest depends on measurements and methods, but all lie in the same general area. Together, they form the lowest points of Earth's crust, the ultimate downward slope where the Pacific Plate dives beneath the Mariana Plate. It is here that the trench reaches its maximum depth, plunging nearly 11,000 meters beneath the surface. To stand on land and look up at the sky, even on a clear day, is to look into distance. But to imagine standing at Challenger Deep and looking up, if such a thing were possible, is to imagine something different. Above you would be not sky, but water. Kilometers upon kilometers of dark ocean stretching upward, pressing down with relentless weight. The distance to the surface is so great that even the largest mountain on Earth would disappear within it. It is a reversal of perspective. Instead of seeing infinity above, you feel infinity above, not light and space, but mass and darkness. For scientists, Challenger Deep is a place of fascination because it is not only the deepest point, but also a place where the Earth itself is in motion. The trench exists because one tectonic plate is sliding beneath another. The Pacific Plate, vast and heavy, is being forced under the Mariana Plate. At Challenger Deep, this process reaches its most dramatic expression. The seafloor buckles and bends downward, pulled into the mantle of the Earth. To study Challenger Deep is to study the living geology of the planet, to see subduction at its most extreme. Earthquakes rumble here, triggered by the grinding of plates. Volcanoes rise in the nearby islands, fed by molten rock created as the sinking plate heats and melts. The deep is not static. It is active, alive with geological energy. Yet geology is only part of the story. Challenger Deep is also an ecosystem. Life, against all odds, thrives in its sediments and waters. Microbes feed on chemicals that seep from rocks. Amphipods scavenge whatever organic material drifts down. Fish patrol the muddy floor, pale and adapted to crushing pressures. The trench is not a barren void, but a hidden world, complete and functioning. For biologists, this is what makes Challenger Deep extraordinary. It shows that life is not confined to the comfortable zones we know. It expands into extremes, into darkness and pressure, into places where we once thought survival impossible. The human relationship with Challenger Deep has always been complicated. On one hand, it represents the ultimate destination, the farthest we can descend without leaving the Earth. On the other hand, it is unreachable for almost everyone. Only a handful of people have ever been there. The dive of Trieste in 1960 was the first. Decades later, filmmaker James Cameron would descend alone in his submersible deep-sea Challenger. Since then, a small number of expeditions have followed, each with robotic or manned vessels, each confirming the depth and exploring small corners of the floor. But in all, fewer people have visited Challenger Deep than have walked on the Moon. The number is still fewer than 30. That rarity gives it symbolic weight. It is not just a place on Earth, but a threshold. To go there is to stand, or rather, to sit encased in a steel sphere at the absolute limit of human exploration within the oceans. Beyond that point, there is nothing deeper. Challenger Deep is the bottom, the end of downward travel. In this sense, it feels as ultimate as space. Astronauts look upward and outward, voyaging into the infinite. Ocean explorers look downward into the finite but crushing abyss and reach its extreme. Both represent the limits of where humans can go. The precise depth of Challenger Deep has been the subject of many surveys, and it still varies slightly depending on method. Different expeditions have reported numbers between about 10,900 and 11,000 meters. These differences come from variations in equipment, calibration, and the challenges of measuring in such extreme conditions. Satellites can estimate depth indirectly by observing the way gravity affects the sea surface, but these measurements lack the fine resolution of sonar. Direct soundings with sonar are more accurate, but even then, tiny differences in water temperature and salinity can alter sound speed and change results. So the trench retains an element of uncertainty. We know it is the deepest point, but we cannot pin it down to a single number with absolute certainty. In a way, that uncertainty adds to its aura. Challenger Deep resists exact definition. It remains elusive even in data. For explorers who have reached it, Challenger Deep is not dramatic in appearance. It is not a gaping hole or a jagged canyon. Instead, it is a flat, muddy plain covered with fine sediments that have drifted down for millions of years. The monotony of the landscape surprises many. You expect extremes and find simplicity. But within that simplicity lies the profound. It is the lowest point on the crust, the absolute bottom. To sit in a submersible there looking out at beige mud is to know that you are deeper than anyone else on Earth. The landscape itself may be plain, but the context makes it extraordinary. Symbolism often attaches itself to places like this. Everest, the highest point, is a magnet for climbers. Challenger Deep, the lowest point, is the parallel. One represents the sky, the other the abyss. Both are extremes. Both carry risks. Both attract those drawn to limits. The difference is that Everest is climbed by hundreds each year. While Challenger Deep remains visited by only a select few, it is not accessible to ordinary adventurers. It requires technology, engineering, funding, and courage. Perhaps that rarity makes it even more symbolic. It is not conquered easily, and so it remains mysterious. For the public imagination, Challenger Deep has often stood as the ultimate unknown. Writers and filmmakers use it as a setting for speculation, a place where monsters might lurk or secrets might be hidden. The reality is quieter, but no less astonishing. Its mystery is not about what people imagine, but about what actually exists. Microbes thriving under unimaginable pressure, amphipods feeding in silence, geological forces reshaping the planet, and human explorers daring to enter, if only briefly. The name itself carries a kind of poetry. Challenger Deep. a reminder that exploration is always a challenge, always pushing into the unknown. A reminder, too, that it is deep, unimaginably so, beyond ordinary comprehension. The combination of the two words encapsulates the spirit of oceanography, the blend of difficulty and wonder. And as soon as you think of its symbolic power, you can see why it drew later explorers back. After Trieste's dive in 1960, decades passed before another human returned. But when James Cameron descended alone in 2012, it was Challenger Deep that called him. He wanted to see with his own eyes what lay at the bottom, to film it, to bring back more than just numbers. For him, as for many, the name itself was an invitation. So, Challenger Deep is not just a location, it is a story, one still being written. Every new expedition adds a sentence, a discovery, a detail. But the core remains the same. It is the deepest place on Earth, the end of downward exploration, a place where geology, biology, and human curiosity meet. Its plain mud floor holds symbolic weight far greater than its appearance suggests. For more than 50 years after the Trieste dive, Challenger Deep remained untouched by human presence. Machines had been lowered, sonar had scanned, but no person had looked out through a viewport at the bottom of the world since Jacques Piccard and Don Walsh in 1960. In that time, astronauts had walked on the moon. Spacecraft had visited the outer planets, and technology had transformed every aspect of human life. Yet, the deepest place on Earth, lying not in the distant cosmos but right here beneath the Pacific, had gone half a century without a visitor. That fact alone fascinated James Cameron, a filmmaker whose career had long been shaped by both storytelling and exploration. Cameron was already known for creating vast, detailed worlds on screen. He had directed films set on alien planets, in futuristic cities, and beneath the ocean. His movie, The Abyss, in 1989, was inspired by his own love of diving and the idea of hidden life deep below the surface. He was also the director of Titanic, a film that drew heavily on his personal expeditions to the wreck itself. For Cameron, filmmaking and exploration were not separate passions. They were two sides of the same drive, to go where few had gone, to see with his own eyes, and to bring back stories for others to experience. So when the opportunity arose to build a new submersible, capable of reaching Challenger Deep, he embraced it. The project took years of design and engineering. Unlike Trieste, which had used a steel sphere slung beneath a float, Cameron's submersible, called Deep Sea Challenger, was sleek and vertical, resembling a green torpedo. It was built to be piloted by a single occupant. That meant that when it descended, Cameron would be alone. The design was revolutionary. Instead of a large float filled with gasoline, Deep Sea Challenger used specially developed syntactic foam, a material filled with tiny hollow spheres that provided buoyancy while withstanding crushing pressure. Its crew sphere, where Cameron would sit, was made of thick steel, barely large enough to fit him, with just enough room for controls and cameras. Outside the sphere, high-definition cameras, robotic arms, and sample containers were mounted, ready to capture both footage and specimens from the trench floor. On March 26, 2012, the dive took place near the Mariana Islands. Cameron climbed into the submersible in the early morning. The hatch was sealed and the vehicle was lowered into the sea. As he began to descend, the world above faded quickly. Sunlight dimmed, then vanished. Hours stretched on as the sub sank deeper and deeper. Cameron later described how the descent felt endless, as if he were falling into another planet. He was cut off from the surface, communicating only through text messages sent slowly by acoustic signals. The deeper he went, the more the pressure mounted. Outside the sphere, the water pressed with more than 1,000 atmospheres of force. But inside, Cameron remained in a bubble of air, surrounded by controls, lights, and cameras. He passed through layers of the ocean few people had ever seen, through zones where bioluminescent creatures flashed briefly outside his viewports. Eventually, he reached the abyssal plain and then finally Challenger Deep itself. The depth gauge showed nearly 10,900 meters. After more than 2.5 hours of descent, he had arrived at the bottom of the world. What he saw was both familiar and astonishing. The seafloor stretched out as a plain of fine sediment, a beige desert beneath black water. Through his lights, Cameron could see small amphipods and other life drifting in the current. He maneuvered the sub to collect samples, filming everything with high-definition cameras. For nearly 3 hours he explored, longer than anyone had ever stayed at such depths. Alone in that small sphere, he became the only person on Earth at that depth, a solitary human presence surrounded by billions of tons of water. Later, Cameron described the experience as one of isolation, but also of awe. The silence, the stillness, the knowledge of where he was all combined into something profound. He compared it to being on another planet, a frontier unexplored, vast and indifferent to human presence. Unlike in spaceflight, where astronauts can at least look out at stars, Cameron's view was of endless darkness broken only by the beam of his own lights. Yet within that beam were creatures, sediments, and formations that told stories about life and geology under unimaginable pressure. His dive was not only a personal achievement, but a scientific one. Samples collected from the trench later revealed microbes with unique adaptations, providing clues about how life survives under such extremes. The footage he captured gave the world its clearest view yet of Challenger. Deep, not as an abstract number, but as a real place. And his success proved that new technology could reach the bottom again, paving the way for future expeditions. For Cameron, the journey was also a way of uniting storytelling with exploration. He had built imaginary worlds on film, but this time he had ventured into one of Earth's real alien landscapes. The images he brought back were not fiction. They were evidence of a frontier still here, still alive, still waiting to be explored. The symbolism of his solo journey also struck many people. Half a century after two men had descended together, one man had gone alone. It was not just an engineering feat, but a reminder of how personal exploration can be. Sitting in a steel sphere the size of a small closet, Cameron had carried with him the curiosity of everyone who had ever wondered what lay at the bottom of the sea. When he surfaced nearly 7 hours after beginning, he was greeted by ships and support crews who had followed his progress. The dive was hailed as a triumph, celebrated not only in scientific circles, but in popular culture. It was a reminder that exploration did not end with the space race, that even on our own planet, there are frontiers as mysterious and demanding as anything beyond Earth. And yet, despite the achievement, the trench still holds most of its secrets. Cameron's dive covered only a tiny fraction of Challenger Deep. The plain he saw was just one part of a vast region. Even now, years later, each expedition reveals new details, new species, new mysteries. His journey was a beginning, not an end. Another step in the slow process of unveiling what lies hidden in the abyss. The dive of deep-sea Challenger reminded the world that the Mariana Trench is not just a line on a chart. It is a place, a real environment that can be visited, studied, and experienced. For Cameron, it was a dream fulfilled. For science, it was a milestone. For the rest of us, it was a glimpse into a world so alien and yet so close. For all the courage it takes to place a person inside a submersible and lower them into the deepest place on Earth, the truth is that most exploration of the Mariana Trench has not been done by people at all. It has been carried out by machines, carefully engineered robots that can go where humans cannot. They do not need air to breathe or light to see. They do not grow tired, nor do they panic in isolation. They are unaffected by the cold, and their metal shells can be designed specifically to withstand the crushing pressure. While human descents remain iconic milestones, the steady work of uncovering the trench has largely been the work of robotic explorers. These machines take many forms. Some are free-falling landers, essentially heavy frames carrying cameras, sensors, and bait to attract life. Lowered into the sea and released, they sink under their own weight, drifting slowly down until they strike the bottom. There, they record whatever they can, transmitting data back to the surface or storing it for later recovery. Others are remotely operated vehicles, ROVs, tethered to ships above by long cables, maneuvered by pilots who sit in control rooms hundreds of meters or kilometers away. And still others are autonomous, programmed to carry out missions on their own, navigating without human direction, making decisions as they go. The first robotic probes to reach Challenger Deep began appearing in the late 20th century, long after Trieste, but before James Cameron's dive. In the 1990s, Japan's remotely operated vehicle, Kaiko, made several descents, capturing video and collecting samples. It was one of the earliest machines capable of reaching the trench repeatedly, and it brought back images of amphipods and other organisms thriving on the seafloor. For the first time, scientists could study the trench in detail, not just for minutes, but for hours, with equipment that could record continuously. Later, the United States developed vehicles like Nereus, a hybrid remotely operated and autonomous system capable of diving to full ocean depth. In 2009, Nereus reached Challenger Deep, gathering data that added to the growing picture of the abyss. But these machines face the same challenges as any human submersible. Pressure remains relentless. Electronics must be protected inside housings built to withstand 1,000 atmospheres. Cables must resist crushing and fraying. Even the best designs sometimes fail. In 2014, Nereus was lost in the Kermadec Trench, crushed by the pressure it was built to endure. The risk of failure is constant, whether the explorer is human or robotic. Despite this, robots have a clear advantage. They can stay much longer than humans. Where a manned submersible may last only a few hours before oxygen and power run low, robotic vehicles can remain for days. They can also be deployed more frequently, each mission adding to a growing dataset. And because they are not limited by human safety, they can be built smaller, more efficient, and sometimes more daring. A robot does not feel fear when descending into darkness. It simply follows its programming. The footage these machines have returned is striking. Images show vast plains of fine sediment, sometimes disturbed by currents, sometimes marked by the trails of animals crawling across the seafloor. Cameras capture amphipods swarming around baited traps, arriving quickly from the shadows. In one descent, scientists observed snailfish, pale and gelatinous, swimming gracefully despite the immense pressure. In another, they recorded unusual jelly-like organisms that drifted slowly past. Each image reveals life in an environment once thought impossible. Robots also bring back samples. Containers are opened and closed at depth, scooping mud, water, or even living organisms. These samples are then studied in laboratories, revealing not only the presence of life, but its adaptations. Some microbes from Challenger Deep are found to metabolize chemicals in unique ways, thriving under pressure that would crush ordinary cells. These discoveries matter beyond curiosity. They inform biotechnology, medicine, and even astrobiology, showing how biological systems can be engineered or how they might function in other extreme environments. The trench is not only a biological frontier, but also a geological one, and robots have contributed here as well. They have mapped the contours of the seafloor with sonar, traced fault lines, and recorded seismic activity. They have helped confirm the dynamics of subduction, the process by which the Pacific Plate dives beneath the Mariana Plate. By studying the sediments and rocks, scientists learn not only about the trench itself, but about the deep workings of Earth's crust. Robotic eyes and instruments turn the invisible into data, and that data reshapes our understanding of the planet. For the people who operate these machines, the experience is different from being inside a submersible. Instead of staring out of a viewport, they sit in control rooms aboard ships watching screens. Cameras transmit images. Joysticks control robotic arms and data streams onto monitors. It may lack the direct sensation of being physically present, but it allows more flexibility. A robotic arm can collect samples with precision. A camera can swivel and zoom. Instruments can run continuously without fatigue. In some ways, robots extend human senses into places we cannot go ourselves. And yet, even with these advantages, there is something uncanny about the work. Pilots describe watching a screen as their vehicle descends into blackness, the lights illuminating only a small patch ahead. It feels as if they are peering into another world, one where the rules are strange and the inhabitants unknown. The knowledge that the machine is kilometers below, connected by a fragile cable, adds to the tension. At any moment, a failure could mean losing the vehicle forever. Each mission carries both excitement and risk. The robots also face the problem of scale. The trench is vast, stretching more than 500 miles. Each descent covers only a tiny portion. Even after decades of robotic missions, most of it remains unexplored. What lies in the hidden folds and slopes is still largely unknown. The robots give us glimpses, but they cannot yet reveal everything. They show us fragments of a picture, pieces of a puzzle that remains incomplete. Still, with every mission, the trench becomes a little less mysterious. Robots have shown us amphipods at depths beyond 10,000 meters. They have revealed snailfish that survive where no other vertebrates are known. They have brought back microbes that defy expectations and sediments that tell stories of earth-shifting plates. Each success builds on the last, creating a mosaic of knowledge. And as technology improves, robots will continue to expand our reach, venturing deeper, staying longer, and mapping more than ever before. For now, though, they remain our most reliable eyes in the abyss. Human dives are rare and symbolic, but robotic dives are steady and practical. They are the daily explorers of the trench, the ones that keep the story moving forward. When robotic vehicles bring back their recordings from the trench, much of the attention naturally falls on the strange creatures moving through the water or crawling over the sediment. But beneath those animals lies something just as important, though less alive: the geology itself. The Mariana Trench is not simply a deep hole, it is the visible scar of an ongoing process, one of the most fundamental in Earth's history. A process that has shaped continents, built mountains, triggered earthquakes, and fueled volcanoes. To understand the trench is to understand the hidden machinery of the planet. The trench exists because of subduction along this stretch of the Pacific Ocean. The Pacific Plate, one of the largest pieces of Earth's outer shell, is slowly sliding beneath the smaller Mariana Plate. The plates move only a few centimeters per year, no faster than fingernails grow, but over millions of years that motion accumulates. One plate is forced downward into the mantle, bending the seafloor into a deep trench as it sinks. The Mariana Trench is the most dramatic example of this process anywhere on Earth, where the downward bend reaches its maximum depth. Imagine Earth's crust as a giant jigsaw puzzle, each piece thousands of kilometers across, floating on the hotter, softer mantle below. These pieces, the tectonic plates, shift and collide, carrying continents and oceans with them. Where they meet, boundaries form. Some boundaries push upward, creating mountain ranges like the Himalayas. Others slide past one another, creating faults like California's San Andreas. But in places like the Mariana Trench, one plate dives beneath another, recycling into the depths of the planet. It is a cycle as old as Earth itself, a conveyor belt of rock that builds and destroys land in equal measure. At Challenger Deep, the Pacific Plate bends sharply downward, sinking into the mantle at an angle. The seafloor here is not flat, but curved, pulled into a long arc. Above, the Mariana Islands mark the edge of the overriding plate, formed by volcanic activity triggered as the subducting plate melts. This chain of islands is a direct result of the trench's existence, proof that the forces beneath the water shape not just the seafloor, but the surface of the Earth. The pressure and heat that act on the sinking plate cause it to release water and other fluids trapped in the rock. When these fluids rise into the mantle above, they lower the melting point of the surrounding material, creating magma. That magma then rises to the surface, fueling volcanoes. The Mariana Islands, with their peaks and ridges, are therefore linked directly to the trench. Without subduction, they would not exist. Geologists study these processes not only to understand the present, but to interpret the past. The rock cycle of subduction and volcanism has been operating for billions of years. It has built continents, reshaped oceans, and controlled the distribution of land and sea. The Mariana Trench is not unique in being a subduction zone, but it is unique in its depth. That makes it an especially valuable window into the mechanics of the planet. Every measurement, every sample of sediment, every record of seismic activity adds to the picture of how Earth works. And earthquakes are an inseparable part of this picture. When plates grind against each other, stress builds. Sometimes that stress releases suddenly, sending shock waves through the crust. The Mariana region is seismically active with earthquakes large and small. Some are barely noticeable, felt only by instruments. Others are powerful enough to shake islands and trigger tsunamis. For the people living in nearby regions, these quakes are reminders that the trench is not just a distant curiosity, but a force with direct impact on human lives. The deep geology of the trench reaches to the surface, its power expressed in sudden bursts of energy. Volcanoes, too, mark the trench's influence. Submarine volcanoes dot the seafloor, some active, some dormant. On land, the Mariana Islands themselves are volcanic in origin, built by repeated eruptions over millions of years. The link between trench and volcano is inseparable. Subduction creates magma, and magma creates volcanoes. To study one is to study the other. But the geology of the trench holds mysteries beyond the visible. Samples taken from sediments reveal not only the history of plate motion, but the history of Earth's climate. As particles settle to the seafloor year after year, they record chemical signatures of the ocean above. By drilling cores and analyzing layers, scientists can reconstruct past temperatures, atmospheric conditions, and even the cycles of ice ages. The trench, in this sense, is a library. Its sediments contain stories written over millions of years, preserved under crushing pressure, waiting for instruments to decode them. Even the rocks themselves carry secrets. Minerals exposed to extreme pressure transform into new forms. Geologists study these high-pressure minerals to understand what happens as crust sinks deep into the mantle. Some of the rarest forms of matter on Earth are created not in laboratories, but in trenches where the natural pressure of kilometers of ocean accomplishes what no machine can easily replicate. Discovering these minerals helps explain the behavior of Earth's interior, the flows of heat and material that drive tectonics. Robotic explorers have helped reveal some of these details. Cameras record landslides tumbling into the trench walls triggered by earthquakes. Sensors detect chemical plumes rising from the seafloor, evidence of fluids escaping from the subducting plate. Seismic instruments record tremors that ripple through the crust, tracing the movement of rock kilometers below. Each measurement adds another thread to the story, weaving together biology, geology, and chemistry into one system. For many, the trench is a reminder of scale, not just in depth, but in time. The processes that created it began millions of years ago and will continue millions more. The Pacific Plate will keep sliding, the trench will keep deepening or shifting, the islands will keep erupting, and earthquakes will continue to rumble. Human lifespans are too short to notice such changes directly, but the geology speaks to vast timescales, the slow heartbeat of the planet. And just as life adapts to darkness and pressure, it also adapts to geology. Hydrothermal vents near subduction zones release chemical-rich fluids, creating oases of life where microbes and larger organisms thrive. These ecosystems depend not on sunlight, but on geology itself, feeding on chemicals from the Earth's crust. In the trench, the line between geology and biology blurs. Rock, water, heat, and life are all connected, each shaping the other. The hidden geology of the trench is therefore not hidden at all, but expressed in countless ways, in the arc of islands above, in the volcanoes that erupt, in the earthquakes that shake, in the sediments that record time, and in the life that flourishes because of the chemistry it provides. To explore the trench is to explore Earth itself, its restless crust, its deep mantle, its cycles of creation and destruction. When scientists speak of life in the trench, they often pause to emphasize how extraordinary it is that it exists at all. At the bottom of the Mariana Trench, pressure is more than 1,000 times what we feel at the surface. Temperatures hover near freezing, sunlight never arrives, and food is scarce. It is a place that combines every extreme condition at once. And yet life not only survives there, it thrives. To study these organisms is to see biology stretch to its absolute edge, to see how far the rules of life can bend before they break. One of the most important forms of life in the trench is also the smallest. Microbes are everywhere in the sediments, packed into mud that looks barren to the naked eye, but under a microscope teems with activity. These microbes do not rely on sunlight. Instead, they feed on chemicals that seep from rocks or on the faint trickle of organic matter that drifts down from the surface. Many of them use chemosynthesis, transforming hydrogen, methane, or sulfur into energy. For them, chemistry replaces light. They're not only survivors, but pioneers, showing that life can be built on foundations entirely different from those we know at the surface. In some cases, these microbes are extremophiles, organisms adapted to pressures and temperatures that would kill most cells instantly. They have proteins specially structured to remain stable under crushing force. Their membranes contain molecules that prevent collapse. Some produce unique enzymes that function only under high pressure, enzymes that fall apart when brought to the surface. These adaptations are so remarkable that scientists study them not only to understand the trench, but to consider what life might look like on other worlds. If microbes can survive here, perhaps they can survive under the ice of Europa or Enceladus, or in the subsurface oceans of other moons and planets. But microbes are not alone. Amphipods, small crustaceans resembling shrimp, swarm at depths beyond 10,000 meters. In baited traps lowered into Challenger Deep, amphipods gather quickly, their translucent bodies shining faintly under lights. They feed on whatever they can find, from drifting marine snow to the carcasses of larger animals that sink from above. Some species of amphipods in the trench have been found with chemicals in their tissues identical to industrial pollutants created by humans, a sign that even at these depths, life is not entirely isolated from the surface world. Still, They thrive, multiplying in conditions that seem hostile beyond measure. Then there are the snailfish, perhaps the most famous vertebrates of the trench. These pale, gelatinous fish look fragile, almost ghost-like, with bodies so soft they would collapse if taken too far upward. But, at depth, they are perfectly suited to their environment. Their skeletons are reduced, their muscles adapted, their cells stabilized by unique chemical compounds. They swim slowly across the seafloor, hunting amphipods and other small prey. Scientists were astonished to discover them at depths exceeding 8,000 meters, where no other fish had ever been seen before. To witness a vertebrate thriving in such conditions is to realize that life's boundaries are broader than expected. Food scarcity shapes everything in the trench. Unlike ecosystems at the surface, which are fueled by sunlight and photosynthesis, the deep relies on the slow rain of organic debris from above. This marine snow drifts downward over weeks or months. Particles of dead plankton, fecal matter, and fragments of larger organisms. Most of it is consumed long before it reaches the abyss. Only a fraction arrives at the sea floor, yet it is enough to sustain entire communities. For animals of the trench, every particle counts. They feed slowly, efficiently, making the most of what little arrives. When larger food sources do appear, such as the sinking carcass of a whale, they become centers of sudden abundance. Scavengers gather in great numbers, stripping the remains until only bones are left. These events may be rare, but they are crucial, injecting bursts of energy into the sparse ecosystem. What makes trench life so compelling is not just its survival, but the adaptations that make it possible. For example, amphipods and snailfish contain a compound called trimethylamine N-oxide, or TMAO. This molecule stabilizes proteins under pressure, preventing them from collapsing. The deeper the species lives, the more TMAO is found in its tissues. It is like a chemical armor, invisible but vital. Such adaptations are precise and elegant, honed over millions of years of evolution. They show that life is not brittle, but resourceful, capable of solving problems that seem insurmountable. The trench also reveals that ecosystems are not limited by the absence of light. On the surface, nearly all life traces back to photosynthesis, to plants and algae converting sunlight into energy. But in the deep, where light never reaches, other pathways dominate. Chemosynthetic microbes form the base of the food chain, just as plants do in forests or grasslands. Larger organisms feed on them or on the organic rain from above, building webs of interaction that function entirely without the sun. It is a different kind of world, one that broadens the very definition of an ecosystem. For scientists, studying these organisms is not only about cataloging species, it is also about learning how biology can be stretched. Every new discovery expands the possible conditions for life. When extremophiles are found thriving in boiling vents or in the crushing cold of the trench, it forces us to reconsider what habitable really means. Planets and moons, once dismissed as lifeless because they lack sunlight, may now be reconsidered. If Earth's own trench holds thriving communities in perpetual night, perhaps life elsewhere does not need a star at all. There is also a humbling element. We often imagine ourselves as the pinnacle of life on Earth, dependent on air, warmth, and light. Yet here are creatures that need none of these, surviving in silence where we cannot. They do not require technology or protection. They are built for their world just as we are built for ours. To them, the trench is not hostile. It is home. And life at the limits is not only about the creatures themselves, but about how they interact with their geology. Fluids seeping from the subducting plate feed microbial communities. Sediments record chemical exchanges between Earth's crust and the ocean. Even the smallest organisms participate in cycles that shape the chemistry of the sea. Biology and geology blend into one continuous system. The more scientists explore, the more they realize that we have seen only the surface. Each new expedition reveals species previously unknown. Some are caught on camera, others in traps, still others detected only by genetic material drifting in the water. The diversity is vast and the majority of it remains undescribed. The trench is not just a limit, it is a frontier, an unexplored realm where life's inventiveness seems endless. And yet, as remarkable as these adaptations are, the story of life at the limits also contains a reminder that the trench is not untouched. Human activity has reached even here. Traces of pollutants, plastics and industrial chemicals have been found in amphipods and sediments at Challenger Deep. These substances travel thousands of kilometers, sinking slowly, spreading invisibly. They show that even the deepest and most extreme environment on Earth is not immune to our influence. Life has adapted to crushing pressure and perpetual darkness. But now it must adapt to pollution as well. Still, resilience defines the trench. Its creatures persist where conditions seem impossible, adapting again and again. They show us that limits are not barriers but thresholds, places where life finds new forms. And once you've seen how life flourishes at such extremes, it becomes natural to ask what happens when human presence intrudes more directly. When scientists first sent cameras and sampling gear into the Mariana Trench, many expected to find an untouched world, a place too remote and too hostile for human impact to reach. After all, it lies beneath nearly 11 kilometers of water, hidden under immense pressure and eternal darkness. It seemed impossible that anything from the surface could make it there. But as the equipment returned and samples were studied, the reality became clear. Even in the deepest abyss on Earth, the footprint of human activity is present. The trench, it turns out, has become a garbage bin, a final resting place for some of the most enduring products of our civilization. One of the first signs came in the form of plastic in 2017. Researchers using remote vehicles filmed a plastic bag resting on the seafloor of Challenger Deep. It lay on the mud like a misplaced ghost of the surface world, stubbornly intact despite years or decades in the ocean. It was not alone. Over time, more items have been found. Food wrappers, bottles, fragments of packaging. These discoveries are unsettling, not because they're unusual, but because they are inevitable. Every year, millions of tons of plastic enter the ocean, carried by currents, broken into fragments, and sinking slowly through the water column. Much of it eventually makes its way downward. Gravity ensures that nothing truly leaves the ocean once it enters. Given enough time, debris drifts to the deepest places. But it isn't just visible trash. Microplastics, particles so small they are almost invisible, have been detected in sediment samples from Challenger Deep. These fragments, worn down from larger pieces, are now part of the very mud in which extremophiles thrive. They have been found in the bodies of amphipods caught in baited traps, showing that plastic is not just present but entering the food chain. Tiny particles of synthetic polymers, products of human industry, now circulate inside creatures living at the very edge of life. Chemicals have made the journey as well. Studies of amphipods from the trench have revealed concentrations of industrial pollutants known as PCBs, polychlorinated biphenyls, at levels higher than in many surface waters. PCBs were widely used in the mid-20th century in electrical equipment, paints and plastics before being banned due to their toxicity and persistence. Yet, because they resist breakdown, they linger in the environment for decades. Released into the air and water, they eventually accumulate in the ocean. Carried by currents and attached to particles, they sink slowly but steadily until they reach the deepest abyss. Once there, they become part of the ecosystem, taken up by amphipods and microbes, cycling through organisms that should have been free of such influence. This reality is sobering. The trench was once imagined as untouched, a frontier beyond human reach. Instead, it has become evidence of how thoroughly our activities affect the planet. Plastics and pollutants that began in factories and cities are now part of the deepest ecosystem on Earth. The abyss has no defenses against them. Life there, adapted to pressure and darkness, has no way to distinguish natural food from fragments of plastic. Microbes that metabolize chemicals now encounter human-made molecules unlike anything in their evolutionary history. The trench, once thought pure, has become a sink for the byproducts of human civilization. And yet, even in this context, life adapts. Amphipods continue to thrive despite ingesting pollutants. Microbes persist in sediments laced with microplastics. This resilience is remarkable, but it does not erase the concern. The adaptations that allow survival may come at costs we do not yet understand. Changes in growth, reproduction, or metabolism could ripple through the fragile food web. The trench, unlike a forest or reef, cannot be easily monitored. Its depths hide the consequences of pollution, making them all the more difficult to study. For explorers, encountering trash at the bottom of the trench is a jarring reminder of human presence. To descend into an environment so alien, so extreme, and to find a plastic bag lying in the mud is to realize that no place is beyond our influence. The sight undermines the idea of the trench as a sanctuary of mystery. It reveals instead a continuity between surface and abyss, a reminder that the ocean is one system connected from shorelines to the deepest points. What enters at the top eventually settles at the bottom. The irony is that these pollutants will outlast us. Plastics can take centuries or longer to break down. Some chemicals may persist even longer. Long after cities change and technologies evolve, fragments of our discarded world will remain in the trench. Future explorers, perhaps centuries from now, may still find traces of today's packaging and sediments. In this sense, the trench has become an archive not only of Earth's natural history, but of human impact. It records not just geology and climate, but civilization's waste. And yet, as troubling as this is, it also connects back to the resilience of life at the limits. Amphipods filled with pollutants still swarm traps. Microbes in tainted mud still metabolize chemicals. The trench continues to function as an ecosystem even with our garbage mixed into its core. Life once again shows its capacity to adapt. But the adaptation is not a justification. It is a warning. Just because life persists does not mean it is unharmed. For scientists, the trench has become both a natural laboratory and a cautionary tale. It demonstrates how pollutants move through the ocean, how they settle, how they enter food webs. Studying it reveals not only the reach of our waste, but the consequences of ignoring it. The trench, once thought to be beyond contamination, is now evidence of the ocean's vulnerability. And yet, in the stillness of its floor, amid amphipods and snailfish, amid sediments shaped by geology and time, fragments of plastic drift quietly. They do not dissolve. They do not vanish. They remain silent markers of our presence, carried into darkness we rarely see. If pollution can reach the deepest ocean, then the trench is not only connected to human activity, but also to questions of life beyond Earth. For the adaptation seen here in creatures surviving in mud laced with plastics and chemicals offer clues to how life might survive in other extreme places. When researchers realized that microbes were thriving in the mud of Challenger Deep, they began to think of the trench not only as a remote part of Earth, but also as a model for other worlds. The conditions there are extreme by any standard. Immense pressure, low temperatures, perpetual darkness, and limited food. Yet life has managed not just to exist, but to carve out entire ecosystems. To scientists who study astrobiology, the search for life elsewhere in the universe, this fact is as important as any telescope image or planetary probe. The deep ocean becomes a mirror, showing how life could emerge and survive in places far from the sun. Consider Europa, one of Jupiter's largest moons. Its surface is covered with a shell of ice, cracked and streaked with patterns formed by tides and heating beneath. Beneath that shell, scientists believe, lies an ocean of liquid water kept from freezing solid by the pull of Jupiter's gravity and the heat generated by its own interior. That ocean may be vast, deeper than all of Earth's oceans combined, but is also sealed beneath ice without sunlight, in a place where the surface is bombarded by radiation. If life exists there, it would have to live in conditions very similar to those of the Mariana Trench, in darkness, under crushing pressure, feeding not on light but on chemical energy. Or take Enceladus, a small moon of Saturn. Plumes of water vapor and ice spray from cracks near its south pole, evidence of another subsurface ocean. Spacecraft have flown through those plumes, detecting salts, organics, and other ingredients for life. Again, sunlight cannot reach that ocean. If organisms exist within it, they would resemble the microbes and animals of the trench more than any life on Earth's surface. They would live in chemical cycles, feeding on reactions between water and rock, thriving in darkness as trench microbes do. The trench teaches us that sunlight is not the only pathway to life. On the surface of Earth, nearly every ecosystem begins with photosynthesis, plants and algae turning light into energy. But in the abyss, life has found another route. Chemosynthesis provides energy without light, just as it might on distant worlds. Hydrothermal vents releasing chemicals from the crust fuel entire communities. Microbes metabolize hydrogen, sulfur, or methane. Larger animals feed on those microbes or on each other. It is a complete system independent of the sun. That independence is the key. It shows that life does not need the conditions we usually assume. Even the adaptations of trench creatures resemble what might be expected elsewhere. Amphipods with flexible bodies that resist collapse. Snailfish with chemical compounds stabilizing their proteins. Microbes with enzymes that only function under high pressure. Each adaptation is a reminder that biology can invent solutions to conditions we might call impossible. If life has done this once, it may do it again in oceans sealed beneath ice on another planet or moon. And so the abyss becomes a stand-in for the cosmos. Scientists send probes into Challenger Deep to learn not only about Earth, but about the universe. Each amphipod caught in a trap, each microbe cultured from sediment becomes a model for what might survive on Europa, Enceladus, or even in the subsurface oceans of exoplanets orbiting distant stars. The trench is both local and universal. The connection extends beyond biology. Just as submersibles are lowered into the trench, spacecraft are sent into space. Both face hostile conditions. Pressure in the ocean, vacuum in space, darkness in the abyss, radiation in orbit. The parallels are striking. Engineers building vehicles for the trench must design for crushing force. Engineers building spacecraft must design for the absence of force. Both must protect delicate instruments inside shells of metal and composite, carrying human curiosity into places humans themselves cannot go. The abyss and the stars are opposite extremes, but the spirit of exploration that drives us toward them is the same. For those who descend into the trench or look through telescopes at the night sky, the feeling is similar. It is a sense of perspective, of realizing how small and fragile we are in comparison to the vast systems around us. In Challenger Deep, the weight of the ocean reminds us of Earth's immensity. In space, the endless stars remind us of the universe's scale. Both experiences inspire awe, humility, and the same question: are we alone? If life exists elsewhere, it may not look like us or like the animals of the surface. It may look instead like microbes in the mud of the trench or like translucent fish drifting in darkness. Perhaps it would glow with bioluminescence, just as deep-sea creatures do. Perhaps it would feed on chemical reactions instead of light. Perhaps it would be as alien to us as amphipods are to forests, and yet perfectly adapted to its own world. Studying the trench helps us prepare for that possibility. It shows us how to look for signs of life in conditions we once thought impossible. Even the silence of the trench offers lessons. Hydrophones capture clicks, groans, and rumbles, signals carried across vast distances. In space, radio telescopes listen for faint signals from distant stars. In both cases, we are listening for signs of activity, of something alive or moving in the dark. The abyss and the cosmos share this. They are places we cannot see directly, but which we can probe with sound and signal, listening for what is otherwise invisible. For many explorers, the psychological experience of the trench also parallels that of space. To sit in a small submersible at Challenger Deep, surrounded by kilometers of water, is to feel isolated from the rest of humanity. Astronauts describe the same sensation in orbit, looking down on Earth from the quiet of space. Both are experiences of separation and perspective, of leaving behind the familiar and entering the unknown. They reveal not only the vastness of the universe or the ocean, but the limits of human perception. And perhaps that is why the trench fascinates not only scientists, but storytellers. Writers, filmmakers, and dreamers have long used the ocean as a metaphor for the cosmos. Its depths, unseen and mysterious, stand in for the unknown stretches of space. The creatures of the abyss inspire images of alien beings. The silence of the deep mirrors the silence between stars. In both cases, we imagine what might be out there hidden beyond our reach. In truth, we do not need to invent. The aliens already exist here in the trench. They are small, resilient, luminous, and strange. They live under conditions as extreme as any we might expect beyond Earth. They remind us that the universe may be filled not with familiar life, but with forms adapted to environments we would call impossible. To find life elsewhere, we may need to think more like a biologist studying amphipods than like a gardener planting seeds in soil. The abyss and the stars are connected not because they are the same, but because they both reveal the possibilities of life and the limits of imagination. The trench shows us that life can exist in darkness under pressure without sunlight. The stars remind us that countless worlds may exist with those same conditions. One is beneath our feet, the other above our heads. Together they frame the question of whether life is rare or common, fragile or inevitable. For as long as humans have looked at the ocean, we've wondered what lay beneath. That curiosity carried sailors across dangerous seas, inspired myths of monsters and gods, and eventually drove scientists to measure depths and invent machines to reach them. Each generation has found new ways to push further, to see what was once hidden. And yet, even with modern technology, most of the trench remains unexplored. The future of exploration is not about closing the book, but about opening it wider with tools and ideas that will take us deeper still. One of the greatest shifts in recent decades has been the rise of unmanned vehicles. Remote-operated and autonomous robots have already transformed our view of the deep, sending back images and samples from places too dangerous or inaccessible for people. The future will almost certainly belong even more to such machines. Engineers are designing submersibles that can dive repeatedly to full ocean depth, equipped with advanced cameras, sensors, and arms capable of delicate sampling. These vehicles will not need recovery after every dive, but could operate for weeks or months at a time, patrolling the trench like silent scouts. Autonomous systems, in particular, promise to change how we study the abyss. Instead of being tethered to ships, they can roam freely, following pre-programmed paths, or even making decisions based on what they encounter. Artificial intelligence may allow them to recognize unusual features, track moving animals, or adjust their missions in real time. The trench could one day be mapped not by a handful of dives, but by fleets of robotic explorers, each covering vast areas, each adding detail to a growing picture of the seafloor and the life upon it. New sensors are also being developed to study the chemistry of the deep with greater precision. Instruments that can measure methane, hydrogen, or other gases in real time will help reveal how geology and biology interact. DNA sequencing technology, once confined to laboratories, may one day be miniaturized and placed directly on submersibles, allowing scientists to identify organisms without bringing them to the surface. Instead of relying on physical specimens alone, we may soon be able to study the genetics of entire communities as they live, capturing their diversity without disturbing them. There are also efforts to bring more people back to the trench, though human exploration will likely remain rare compared to robotics. New deep-diving submersibles are being built with improved safety, comfort, and endurance. Some designs imagine transparent spheres, offering panoramic views of the abyss instead of narrow portholes. Others envision vehicles that can carry multiple passengers, turning the journey from a solitary mission into a shared experience. For those few who will ever descend, the future may offer a chance to see the trench more clearly, to experience its silence and pressure in ways Pickard, Walsh, and Cameron could only dream of. Another frontier lies in international collaboration. Just as space exploration has increasingly become a global effort, so too may the study of the deep ocean. Nations with advanced technology, Japan, the United States, China, and others, are already investing in deep-sea vehicles. In the future, combined efforts may create networks of monitoring stations on the seafloor, permanent observatories that record data continuously. These could track seismic activity, chemical changes, and biological communities over years or decades, providing a living record of how the trench evolves. Instead of snapshots from brief visits, we would have an ongoing story. At the same time, new materials are being developed to withstand pressure more efficiently. Alloys stronger than steel, ceramics with remarkable toughness, and composites designed at the molecular level could make future vehicles lighter, faster, and more reliable. Advances in battery technology will allow longer missions, while improvements in communication may make real-time control possible even at full ocean depth. These incremental changes add up to something profound, the possibility that the trench may become as regularly accessible to science as space is today. The question of resources also looms in the future. Some view the trench and other deep ocean regions as potential sites for mining, rich in metals and rare earth elements, vital for modern technology. Nodules of manganese, cobalt, and nickel lie scattered on the seafloor in some areas, formed over millions of years. Mining them could fuel industries on the surface, but the environmental cost is uncertain. The ecosystems of the deep are fragile, slow to recover, and often poorly understood. The debate over whether to exploit or protect the trench will likely intensify. The future of exploration is not only about discovery, but also about decisions. Choices between curiosity and consumption, between knowledge and extraction. Education and culture will play roles as well, as more images and stories from the trench reach the public. Fascination with the deep will grow. Virtual reality may allow people to experience what it feels like to descend, to look around at the mud plains and glowing creatures without leaving their homes. Documentaries, films, and interactive displays will continue to bring the abyss into classrooms and living rooms, turning a remote frontier into a shared human experience. The trench, once imagined only in myth, may become part of everyday knowledge. And yet, for all these advancements, mystery will remain. No matter how many robots we send, no matter how detailed our maps become, the trench is too vast and too dynamic ever to be fully known. There will always be new species, new geologic features, new chemical mysteries hidden in its folds. The future of exploration is therefore not about reaching an end, but about accepting that the end does not exist. The trench will always hold more. It is also possible that by studying the trench, we will learn not only about the ocean, but about ourselves. Just as space exploration has inspired reflection on humanity's place in the universe, deep-sea exploration may inspire reflection on our place on Earth. To look at the trench is to see resilience and fragility side by side. Ecosystems that survive impossible pressure, yet that show traces of our pollution. To descend into it is to see both nature's endurance and humanity's reach. The future of exploration will not just be about data, it will also be about meaning. When you think back over everything hidden in the Mariana Trench, it becomes clear that this single scar in the seafloor is more than just depth. It is a place where pressure, darkness, and silence combine into an environment that reshapes life itself. It is a reminder that Earth is still filled with mysteries, that even now, in an age of satellites and spacecraft, most of our own planet remains unseen. The trench is a frontier, but not one marked by flags or borders. It is a frontier of knowledge, of imagination, of humility. When explorers first measured its depth, they did so with little more than ropes and weights, astonished at the numbers that came back. When Pickard and Wolfe descended in Trieste, they carried with them the weight of human curiosity, proving that even the deepest abyss could be reached. When James Cameron followed half a century later alone in Deep-Sea Challenger, he showed that the trench is not only an obstacle but also an invitation. And now, with fleets of robots and sensors, the trench is slowly unfolding its secrets. Piece by piece, sediment by sediment, species by species. But no matter how much we learn, the trench remains what it has always been, a place beyond ordinary experience. To imagine yourself at the bottom is to imagine a silence so complete that only distant rumbles break it. It is to imagine a blackness so perfect that your own lights reveal only a bubble of mud and drifting creatures before fading into nothing. It is to feel, even in imagination, the weight of the ocean pressing down from every direction, a reminder of forces greater than ourselves. And within that weight and silence lies resilience. Microbes turning chemistry into life, amphipods swarming over scarce food, snailfish gliding with fragile grace. Each adaptation is a small triumph, proof that life is not fragile but inventive, not limited but expansive. The trench shows us not what ends life, but what reshapes it, bending biology into new forms that seem alien, yet a part of our own world. It is also a mirror. In the plastic fragments caught in sediments, in the pollutants measured in amphipods, we see traces of ourselves. Even the deepest places are touched by human hands, though those hands never reach directly. The trench reflects back to us our reach and our responsibility. It asks us to see that our actions travel farther than we think, settling quietly in places we will never visit. And it is a bridge. The trench links Earth to the stars, showing that life does not depend on light, that it can exist in extremes, that it can adapt to pressures and chemistries that once seemed impossible. In the darkness of Challenger Deep, we glimpse the possibility of life on Europa, Enceladus, or worlds beyond. The abyss beneath our oceans and the abyss above our skies are not separate, but connected by the same question: where else can life be? For centuries, myths filled the deep with serpents and gods, with monsters and palaces. Today, science has filled it with data, images, and discoveries. But the feeling it inspires remains the same. Whether imagined as a kingdom of spirits or as a realm of amphipods and snailfish, the trench is still a place that humbles us, that expands our imagination, that reminds us of what we do not yet know. So, as we drift with this thought, picture yourself lowering slowly through the water, sinking past the last beams of sunlight, past the twilight zone where blue fades into black, past the zones where whales dive and squid drift into the perpetual night. Imagine descending through kilometers of silence until at last you reach a plain of mud, flat and quiet, stretching into darkness. Around you, tiny creatures move, glowing faintly, feeding in silence. Above you, the ocean rises for 11 kilometers, a column of water pressing down. And within that place, life continues, indifferent to whether we watch or not. There is something calming in this. The trench is not a story of conquest or control. It is a story of presence, of existence. It has been there for millions of years and will remain long after us. Our explorations are brief visits, our instruments brief glances. But the trench does not depend on us. It simply is. It waits in silence, holding its mysteries, shaping its creatures, recording its sediments, listening to the distant rumbles of earthquakes and storms. And in that waiting, it offers us perspective. It reminds us that the earth is larger and older than our imaginations, that life is stronger and stranger than we expect. That exploration is less about finding ends than about encountering continuities. The trench is not the bottom of knowledge. It is the beginning of wonder. So let yourself drift into that wonder, into the thought of a place so deep that light has never touched it, so pressurized that even steel must groan, so silent that only distant echoes pass through. Picture the amphipods circling slowly, the snailfish gliding, the microbes working unseen. Picture the mud plains stretching endlessly. Picture the darkness holding it all, complete and calm. And as you imagine, let the thoughts settle like sediment itself. Layer upon layer forming slowly, quietly, until it feels part of you. You're not at the surface now. You're not bound by the noise of waves or the brightness of sun. You're drifting calmly into the deep. Thank you for spending this time exploring with me. If you found this journey soothing, if it kept you company, or if it helped you drift a little closer to sleep, you're always welcome to return here whenever you need it. And if you'd like to hear more quiet explorations like this, you can follow along by subscribing or by leaving a small sign of support. It helps keep these voyages going so that together we can keep wandering into mysteries of science and the calm they bring. For now, let your thoughts settle like the sediments of the ocean floor. There's nothing else you need to do. Just let your breath slow. Let the weight of the day sink away. And if sleep comes, let it take you gently, as if you were drifting deeper into the quiet of the trench itself. Good night, and until next time, may your rest be as calm as the deepest waters.